Hello all Royal Rangers, my name is Commander Matthew Kenslow and I'm over here in the United States of America, and I've been a Royal Ranger for 20 years and year number 7 as a commander. Thank you so much for checking out this video. The purpose of this video is to go over a merit. In these videos I'm going to walk through every one of the requirements. Now it's important to note that while watching these videos it will not give you the merit. You have to show to your commander that you have watched and learned from these videos. What I recommend you doing is taking down notes for each requirement and then show them to your commander for approval. Some of the purposes of Royal Rangers is to build knowledge, wisdom, skills, and leadership attributes while learning about God's Word and conserving His resources practically. And most importantly, to have fun doing it. So I'm Commander Matthew Kenslow from the United States of America, and be blessed. Hello everybody, welcome to the Astronomy Merit. Let's begin with requirement 1, define astronomy and name 2 important astronomers. Astronomy is the scientific study of everything beyond Earth's atmosphere. Astronomers study the stars, moons, planets, and other celestial objects that we will define in requirement 2. Going back almost 2,000 years ago, you had a man from Egypt named Ptolemy. And back in the day, people held the view of a geocentric model, or Earth-centered. Geo means Earth, centric meaning centered, so people believed that the Earth was at the center of the entire universe. And that kind of it made sense that they would think that back then, because if you go outside, you see all the stars going around you, you see the sun going around you, you see the zodiacal constellations going around you. So people assumed that the Earth is at the center of the universe, until Nicholas Copernicus came along and he held a heliocentric model. Helios means sun, and centric meaning centered, so heliocentric means sun-centered. And he was one of the early proponents of this model, that the sun was at the center of the solar system, and Earth goes around the sun, yet the moon still goes around the Earth. Copernicus wasn't entirely accurate. I believe that he thought that all the planets and the moons go around in circular orbits, which when we talk about Kepler here shortly, it doesn't go in circular orbits. Now, Copernicus was a Roman Catholic born in Poland, and the Roman Catholic Church kind of held the geocentric model, and anybody that challenged that could be at a risk of maybe excommunication, death, or house arrest, or such like that. So Copernicus had his works published posthumously, which means after his death. So after his death in 1543, that's when his works were published. Next is Galileo Galilei. He is another Roman Catholic, but from Italy. He built his own telescope. He probably wasn't the inventor of the telescope, but he built his own. He further proved the heliocentric model. He also discovered the moons around Jupiter. We call them the Galilean moons. And if you look at the notes on the right, that this is Galileo's actual notes. The circles that you see are Jupiter in these days, and the asterisk are stars that he saw, or what he thought were stars. It was later shown that these were moons, not stars, and he observed these moons relative to where Jupiter was. So on this day, we have 1 moon on the left and 2 on the right. On this day, we have 3 on the left and 1 on the right. And there's a total of 4, Europa, Ganymede, Io, and Callisto, which we'll talk about later in requirement 3. He also discovered the Venusian phases. Just like the lunar phases, which we'll talk about in requirement 8, Venus has phases because in our perspective, Venus goes around the sun, and based on where Venus is at in its orbit, it could be a crescent, it could be half, it could be a gibbous, it could be a full. So he kind of discovered that. if you notice, the further away it is, the smaller it goes. But the smaller it goes, the more full it appears. When Venus is in front of the Sun, it's closer to Earth, but we can only see slivers or up to a half. Unfortunately, he faced the Roman Inquisition, like I was just talking about the Roman Catholic Church back when we were talking about Copernicus, and he was sentenced to house arrest for the final decade of his life. Next is Johannes Kepler. He was a Lutheran from Germany, which makes sense. That's where Martin Luther was at, where he nailed the 95 Theses on the church doors, and he translated the original Bible into German for the common people. Anyway, Kepler published his 3 laws of planetary motion, the first 2 in 1609 and the last one a decade later. He was actually a student of another astronomer that you could do more research about, Tycho Brahe, and it's kind of interesting if you decide to research Tycho. I believe he had a golden nose because he lost part of it in a duel, and he also built a huge observatory, I believe, that could measure the positions of celestial objects like planets and stars down to the finest of detail. So I will summarize this most definitely. Kepler's first law basically says that the planets go around the Sun in elliptical orbits. An ellipse is like a squashed circle, or basically an oval shaped. Kepler's second law basically says that as the planets orbit around the Sun, it's going to orbit faster than if it's far away from the Sun. So if you could follow the laser pointer here, here it's slowing down a little bit, and then as it gets closer to the Sun, it speeds up, and then it slows back down. And this has everything to do with astrophysics and the gravitational pull and everything, which I find very amazing that Kepler studied this in the 1600s, but also that the planet sweeps out an equal area of the same time. So to break that down, from this position to that position is the same amount of time that it takes the planet to go from this position to that position. This arc length, as you see, is longer than here, but it's still the same amount of time. Also, if you were to imagine to color this in, the same amount of crayon or marker that you use to shade this would be equal to the amount of crayon or marker that it would take to shade this in. In other words, equal area. And that's kind of maybe actually more advanced than you need to know, but anyway. Kepler's third law basically says that as planets go farther from the Sun, the slower its orbital velocity. So for example, Earth goes around the Sun once a year. Well, obviously. Mars about once every 2 years. Jupiter once every 12 years. But it's not because it's further away from the Sun, but they are actually traveling slower. So the Earth goes around the Sun about 67,000 miles per hour. The farther out you go, the planets are going slower. And that's essentially what's encapsulated in Kepler's third law. Now moving into modern times, in the past century, we have Edwin Hubble from the United States of America. He proved that the universe is expanding. How did he do that? He was measuring the redshifts of galaxies. So one night he went out, looked through his telescope, in this case a very giant telescope, of course, not one of those simple ones, and he was measuring the redshifts of stars. What does that mean? Well, essentially light travels in waves, kind of like this. It goes up and then down, then up, down, and depending on the wavelength, we could perceive a color if it's in a certain range. Some wavelengths are too short or too wide for us to perceive the color, but if it's in a specific range, then we could see red, orange, yellow, green, blue, violet. Well, the longer the wavelength is stretched, so let's imagine that it goes up and then it stretches, and now the wavelength is longer, it becomes more red. It becomes redder. In order for this to be possible, the galaxies are moving away from us. That's stretching the wavelength that's called a redshift, and therefore the universe is expanding. He said that some galaxies are moving away from us, other galaxies are moving away from us faster, and even more distant galaxies are moving away from us faster than the speed of light. And in turn, he kind of proved the Bible is true. I've tried to research this. I can't find out whether he was a Christian or not, but he did validate the Bible when it says in all these passages that the Lord stretches out the heavens. And you could pause if you want to read each of these one by one, but God does stretch out the heavens, and an interpretation of that is an expanding universe. Okay, now let's go to Isaac Newton and Albert Einstein. Centuries apart, but what do they all have in common? Gravity. So Newton discovered the concept of gravity supposedly by an apple that fell on his head. That didn't really happen, but he probably saw an apple fall and started to think, well, what was the velocity at 2.78 seconds? And that was the birth of calculus. But Albert Einstein published his work to prove how it actually worked. That's called the General Theory of Relativity, November 25th, 1915. And one of the most amazing things, in my opinion, is that on November 25th, 2015, I was in astronomy class in the fall 2015 semester at OCC, and I was in astronomy class on the centennial, or the century anniversary of this work being published. But anyway, the concept of gravity is that, well, objects fall and are attracted toward the center of the Earth, basically. Gravity isn't, things falling down, because if you could imagine a globe and you're standing up here, okay, well, you're standing because gravity pulls you downward, right? Well, what about people in the South Pole? Okay, according to you, the people in the South Pole should be falling off the Earth. But no, the people in the South Pole are standing and are being attracted upward. Okay, well, how does that work? The real definition of gravity is that it pulls things toward the center of the mass, in this case, the Earth. So it doesn't pull downward, it just pulls in that direction relative to where we're standing toward the center of the globe. So for Einstein's general theory of relativity, think about a sheet. Okay, just like a square sheet. Okay, you stretch it out, one person on each corner. Okay, and it's flat. Well, now imagine dropping a marble down here. Okay, it's going to curve that sheet, or that fabric, right? Well, here's another illustration of that. You have a sheet or a fabric, and you have three different masses, all of a different mass, and they're each curving the fabric right here. Now, imagine shooting off an object in this direction. Well, it's just going to go right by, right? But if another object comes in starting over here, now take a look at what happens. It gets sucked into the gravity, all right? And this creates orbit. Now, there's a YouTube demonstration, or probably a lot of them, that you could see this happening with like a basketball and marbles. If you do this with marbles, it will always crash into the larger object. Well, obviously in real life that doesn't happen. I'm sure there's other laws of astrophysics, but it's basically the concept of why things orbit around. We call this sheet space-time. And guess what? The smaller objects also curve this fabric of space-time. And if you could imagine a smaller object coming in this way, it's going to be pulled into its gravity, and those are called satellites or moons and such. And then imagine that this red ball is, let's say, Mars. Mars has two asteroid-shaped satellites or moons caught in its gravity, and then in turn Mars is caught in Sun's gravity and is orbiting the Sun. That's basically how gravity works in a nutshell. Okay, requirement 2. Explain the major differences between the following. planets, moons, stars, comets, asteroids, meteoroids, solar systems, and galaxies. So let's begin with the definition of planets. So planets are small, dark bodies that orbit a star. They're made up of either rock or gas. And they don't emit visible light, which is why they're known as dark bodies. Rather, they reflect light from the sun. The sun has enough energy or fusion in its core to emit light, and all the planets and moons reflect the light. Now note that they don't emit visible light, but they can emit light, just in the wavelengths that we can't see. Remember back when we were talking about waves and the redshift? Well, this is when the waves are even further stretched, increasing the wavelength, that they're known as infrared light. Infra means below, infrared, below red. So these are long wavelengths that we cannot perceive, and in fact, infrared light is basically heat. So planets can emit heat, which is a form of light or energy. Just be a bit technical. That's what my astronomy professor taught me, and he has a doctorate in astronomy. Next are moons, or natural satellites. A satellite is something that orbits around something, and when we put out satellites up in space to orbit Earth, we call that satellites, or, well, man-made satellites. Well, moons are known as natural satellites, or non-man-made satellites. They're also small, dark celestial bodies that orbit planets. So the key takeaway is that satellites go around planets, planets go around the stars, and both planets and satellites reflect the sun's light. Now let's talk about the stars, such as our sun. If you notice here, this is a very famous open cluster known as the Pleiades. And if you are familiar with Subaru, which is a car brand, it kind of looks, the logo looks like a familiar open cluster. Well, Subaru is Japanese for the Pleiades or the Seven Sisters, just for some trivia. Stars are large balls of gas that emit light and produce heat. Anyway, in order to be a star, it must be at least 8% the solar mass relative to our sun in order to be a star. So our sun is very massive, which we'll talk about shortly. And if you have something that is 8% that of the sun in terms of mass, then it qualifies a star. Below which you don't really have a star, you have something more like a brown dwarf, which you could think of as a failed star. It's not a star, it's not a gas giant planet necessarily, but it just doesn't have enough mass to generate fusion in its core, which we'll briefly talk about later. Our sun makes up 99.86% of the solar system's mass. Our solar system is composed of, well, our sun, all the planets and asteroids and comets and meteoroids, which we'll define later. Well, if you take the entire solar system and add up the mass, 99.86% of the mass comes from our sun. The sun is over 1,000 times as massive as the planet Jupiter. So some people wonder, how close is Jupiter away from becoming a star? Well, it's still quite a ways away, because if Jupiter had about 13 times more mass than it does already, then it could qualify as the aforementioned brown dwarf star. And it needs to be approximately 80 times its own mass to qualify as a simple red dwarf star. So still, Jupiter would need a lot more mass in order to fuse the hydrogen into helium in its core, which is getting a little bit ahead of myself. So here are the layers of the sun. You have the core, which is about 27 million degrees Fahrenheit. You have the radiative zone, the convective zone, and then the outer layers, such as the photosphere and the chromosphere, which could be almost 6,000 degrees, or almost 10,000 degrees Fahrenheit, actually. And then you have the corona, or like this atmosphere around it, the sun shoots off not just light and heat, but also solar wind and solar radiation, which we'll come back to when we talk about comets. So what goes on inside the core of the sun, which causes all this energy to be released? What causes the sun to emit light and heat energy? Well, it's all because of the fusion in the core. So a simple way to think about this is you probably worked with modeling clay before, clay or Play-Doh. Imagine putting two small pieces of clay together and fusing them into one. Well, that's called fusion. And when you do that, complicated process short, because it's not as easy as this, because I studied it, it's not this easy. That produces energy, and that energy is in the form of heat and light. What's interesting is that there are 600 million tons of hydrogen being fused into 596 million tons of helium every single second inside the core of the sun, and it makes its way all the way to the surface of the sun and then gets emitted out. Okay, but if you think about it, that's a 4 million ton difference. Okay, where did that 4 million tons go? Did it just disappear? Well, if you study science in the future, you'll learn about the conservation of matter, in which or the conservation of mass, in which matter is neither created nor destroyed, but it could be converted. Well, guess what? That 4 million tons gets converted into energy every single second, and therefore E equals mc squared. Okay, well, basically it means that energy and mass could be converted into the other. So energy could be converted into mass, and mass into energy, and then the C in the famous special theory of relativity that Einstein published in 1905 stands for the speed of light. So C is the speed of light, which we'll talk about later in a future requirement here. Now, if you could imagine all that energy pushing outward from the nuclear fusion in the core, how is it that the sun or any star stays intact? Well, it's the gravitational pull. The star's own gravity is pushing inward, and they just so happen to equally counterbalance each other out, and that is called hydrostatic equilibrium. Equilibrium meaning that both forces which are going in opposite direction are equal to each other, and that's what keeps the star from collapsing in on itself or just blowing off all its layers. So these are the insides of the gas giants, Jupiter, Saturn, Uranus, and Neptune, which we'll talk about in requirement 3. It's typically hydrogen and helium, especially the first two gas giants, and then the last two includes methane, which we'll talk about later on as well. Also some amounts of ammonia and water, and it's theorized that there is a rocky, icy core in the center. But again, with all the hydrogen and helium, how is it that the hydrogen inside these four gas giants aren't fusing into helium, thereby producing light of its own? It's because it's not massive enough. Alright, now let's get on to comets. Okay, so comets are chunks of ice, rock, and dust that orbit the sun. A nickname is hairy star or dirty snowball. Comet comes from coma, which is Latin and Greek for hair. Kind of a bit like Coma Berenices, I believe you pronounce it. It's a constellation of a woman's hair. Just to say, we'll talk about constellations in the future. Again, it could be nicknamed either hairy star or dirty snowball, because if you look at it either with the unaided eye or a telescope, it looks a bit fuzzy, so hairy star. Also the tails of the comets kind of looks like hair as well. There are a few types of comets. There are short-term comets, which orbit the sun every less than 200 years, like Halley's Comet, which we'll talk about later. And then there are long-term comets that orbit around the sun once every 200 years. And then there's other comets that are interstellar travelers, which means that they just pass by the sun once. And why? Well, it's because that while they're journeying through our galaxy, they get attracted to each star's gravity, depending on how close it is, and sometimes they are attracted to our sun, they pass by, and then they're on their merry way. Here is the famous Halley's Comet in 1986. My grandfather actually saw Halley's Comet some 9 years before I was born. And the next return is said to be in 2061. Here is a tapestry from the 11th century about, and this is the first known depiction of Halley's Comet, as you see right there. So comets were viewed as harbingers of either good luck or bad luck. You could do more research if you want about that. But after centuries of seeing this famous comet, Halley's Comet, an astronomer, started to think, well, could this be the same comet? Because this one comet kept appearing every 75 to 76 years. Could it be the same one? So he made a prediction saying, I believe this comet is going to come in this year, but unfortunately he died before, but people still checked it out and the comet returned, and therefore this famous comet that had been seen all these centuries was the same comet. Of course, not all comets are the same, but this one that comes by every like 75 to 76 years, Halley's Comet, is one of the most famous comets. And that's because it's at a fixed orbit around the sun. So where did comets come from? Well, they come from beyond the orbit of Neptune, known as the Kuiper Belt. That's where Pluto and Eris and Makemake and all the other dwarf planets, except for Ceres, which we'll talk about later, reside in. So this is very far away from the sun, therefore it's very cold, and that's why you have chunks of ice in this region here, or this belt. So there are two main tails to a lot of comets. Not all comets have a tail, but some of the larger ones do. First, for some nomenclature, you have the nucleus, which is the comet itself. You have the atmosphere around the comet, known as the coma, and you have two main tails, the dust tail and the gas tail, also known as the plasma tail, or the ion tail. The comet's coma arises because the ice vaporizes the closer it is to the sun. The coma can get up to 15 times the diameter of Earth, and there was one coma that was recorded to be about the diameter of the sun, so that's how huge it was. The diameter of the sun, I believe, is 864,000 miles. And when I was taking an astronomy lab in the summer of 2016, we looked at the sun through solar telescopes tons and tons of times and made observations and recordings and trigonometry and all that, to where I will never forget that the diameter is 864,000 miles, or approximately that distance. So tails could be hundreds of millions of miles long, which is longer than the distance between the sun and the Earth, if you could imagine that. So the plasma tail, or the ion tail right here, is caused by the solar wind. So the solar wind is made up of these fast-moving charged or electrical particles that escape from the sun and out into space. So protons and electrons, basically, or positively charged particles and negatively charged particles, respectively. And when these are blasted out of the sun and out into space, they could travel at over 1 million miles per hour approximately. The solar wind is also responsible for the auroras, aurora borealis and aurora australis. These charged particles enter the magnetosphere at the weakest part of Earth, and the weakest part of the magnetosphere is at the poles. The charged particles interact with the molecules up in the sky, in our atmosphere, causing the auroras, or the northern and southern lights. And finally, you have the dust tail right here, and this is caused by solar radiation and radiation pressure. Essentially, the light and the heat and other radiation that comes from the sun or energy, that produces the dust tail. Now I want you to notice that as the comet gets closer to the sun, that's when the tail forms, and that as it goes around the sun, the tails get longer and longer, and they always point away from the sun, because the sun is blasting all this radiation and solar wind outward in all directions in 3 dimensions, and it's pushing the tail away from itself, away from the sun. Here's a close-up of a comet, and here are even more close-up pictures of a comet. Okay, now asteroids. Aster means star, kind of a bit like an asterisk. So that's where that name comes from. And oid means like, or having the likeness of, or resembling. So an asteroid resembles a star, or has the likeness of a star. And that's because if you look at an asteroid through a telescope, it will look like a star. Why? It's because the asteroid is reflecting light from our sun, making it look like a star. But upon closer inspection, it's actually not a star, but it's not a planet either, so we call it asteroids. They're also known as minor planets. And these are small planet-like bodies that orbit the sun in the asteroid belt, which is beyond the orbit of Mars. So asteroids are in the asteroid belt, comets are in the Kuiper belt. These are composed of rock and metal, and remember that that comets are primarily composed of ice, along with other things in its composition. There are over 1 million of them, but if you were to put all the asteroids together into like one big object, it would be smaller than our moon. And they are far apart, however. If you were to step on an asteroid, you probably wouldn't see another one for several hundreds of miles away. They are typically 2.5 times the distance from the Earth and the Moon from each other. So it's not like one of those science fiction games or movies that you may have watched where people are dodging all these asteroids close by one another. It's not really like that in real life. So here's another picture of an asteroid, and I want you to take a closer look. That is a satellite. So some asteroids are big enough to have its own satellite, like planets and their satellites. Now, what is this? This is Ceres. This is actually an asteroid and a dwarf planet. It's the largest asteroid, and it's the only planetary body that's both an asteroid and a dwarf planet. Why isn't it just a planet, a terrestrial planet? Well, to be a planet, it needs to be round, okay, that checks, okay. It has to orbit the star, our sun, that checks, okay, but it doesn't clear its orbital path. There are other asteroids in the way of its orbital path, thereby demoting it from planet status. So it's just one of those dwarf planets. Okay, now on to meteoroids. Meteor is Greek for of the air or of the atmosphere. Think about meteorology, the study of the weather in our atmosphere. These are small pieces of space debris that come from comets and asteroids, which we just defined, so you should know all about comets and asteroids, where they come from, their composition and such by now. Most meteoroids are the size of a grain of sand. As it enters our atmosphere, the speeds range from 25,000 to 160,000 miles per hour. And that causes it to burn up in our atmosphere. The friction, from what I've been taught, as it goes through our atmosphere causes it to burn up, because friction, like rubbing hands together, produces heat. So now I want to clear up any confusion between terminology. You have meteoroids, meteors, and meteorites. Okay, what's the difference? Well, here you have an actual meteoroid out in space. Once it enters our atmosphere, it burns up, and we see it as a falling star or a shooting star. It's not really a star, but we call that a meteor. Like, there goes a meteor. Okay, now, Once it hits our planet, it could splash in the ocean, or it could land on Earth, and we call that a meteorite. And this is a tektite, which I borrowed from one of my commanders when I taught the Astronomy Merit for the second time in the spring of 2019 to the boys. And I had them hold something from outer space, which I thought would make it very special. Recall the two principal sources from which meteoroids originate. You got asteroids and you got comets. Well, the meteoroids that come from comets are more reliable to clock down so that you could set it on your calendar and go out one night and see a bunch of meteors, and we call that a meteor shower. How that works is that as a comet comes around the sun, some of it completely intersects Earth's orbit like this. And as the comet goes around the sun, with the radiation and the solar wind of the sun creating the tail, pieces of the comet are left behind floating around in space. And so every year, as the Earth goes around the sun, it's going to pass through several comet trails. And therefore, some of the pieces that are floating around in here are kind of going to be ran into by Earth's atmosphere. And then the meteoroids are going to burn up. We call that a meteor. And we have a meteor shower. So meteor showers are a result of comets. And some of them are the Orionids, Leonids, Taurids, Geminids, Ursids. And they're so named from the constellations that they radiate from, which I'll get to in a few moments. This table tells you the best time to view it, whether it's pre-dawn or late evening or all night. Usually it's around 1, 2, 3 o'clock in the morning. And here are the number of meteors you could see per hour. And these are the dates or the date ranges that you could see on a calendar, or specifically an astronomy calendar, so that you could go out at a certain part of the night and get to see a bunch of meteors. And this tells you what direction you should face, whether you should face north, south, northwest, etc. And recall that these principal meteor showers arrive at the same time of the year every single year. So they're reliable, therefore they are associated with the comet. And these are the different comets. For example, Halley's Comet, as it goes around the sun once every 75, 76 years, it leaves a trail of meteoroids behind, and then Earth pretty much slams into it, causes a meteor shower. And for Halley's Comet, that occurs on May 4th, as well as October 21st to the 22nd. So let's say it's October 21st, and you're looking up at the constellation Orion. That's why it's called Orionid. You're actually going to see meteors that were meteoroids that came from Halley's Comet, for example. So here's how we name the different meteor showers. This is the Orionids, and it's so named because it's in the Orion constellation. More on that in a future requirement. And then you have, again, the Taurids, which of course would be radiating from Taurus, which is by Orion. And then the Leonids by Leo, and Andromedids by Andromeda, and Geminids by Gemini, etc. This is called the radiant, is because the meteors seem to be radiating from a single point right here, kind of a bit like the sun rays, how sun rays radiate outward like this, going to appear to come from a point right around here in Orion. Here is a GIF of a huge meteor that struck in Russia, I believe, on February 15th, 2013. I was actually a senior in high school at the time, all the way in the United States, and I remember when this story broke, and it caused a lot of damage too. Here's the Hoba meteorite in Namibia. This is a giant piece of space rock that did not shatter into many different pieces, and it's in Namibia, Africa, and it weighs 60 tons, or about 120,000 pounds. So imagine that making it through our atmosphere and then landing on Earth as a meteorite. I mean, a lot of meteoroids burn up in our atmosphere once it becomes meteors, and then it just almost disintegrates, and they become very small and tiny. Imagine this thing surviving all of that and landing on Earth. In fact, this is Meteor Crater, also known as the Barringer Crater, in northern Arizona. And this is a result of a giant meteor, and it's about 560 feet deep. And it's about 20 football fields wide, or just less than a mile. And here's a picture of it from either a high altitude or from space. Next is the solar system. A solar system is a star, such as our sun, and all the planets, asteroids, meteoroids, and comets which orbit that star, such as our sun. This is our home solar system, or sun system as it's also called, and many other stars in our universe has its own solar system, which includes its own asteroids, meteoroids, and comets and such. So no, we're not alone in terms of solar systems. And also you now know how to define planets, asteroids, meteoroids, and comets, and what are the differences. Remember, an asteroid is between the orbits of Mars and Jupiter, and they're usually rocky, whereas comets are usually icy because they originate from beyond the orbit of Neptune. And then pieces of asteroids and comets are called meteoroids. And also there are satellites, so don't forget about that, the satellites that go around the planets. Galaxies. A galaxy is a group of stars bounded together by gravity and spin together through space. There are typically millions to trillions of stars per galaxy. There's about a few 100 billion stars in our galaxy, and the Andromeda galaxy has about 1 trillion stars in it. The Andromeda galaxy is the nearest spiral galaxy like our own. And ours is called the Milky Way, kind of a bit like the candy bar. So here's a picture of the Milky Way that you could see in less light polluted areas. And also, the best place to view meteor showers is in less light polluted areas. So not really in the city, basically. You could go out into the country or mountains or deserts and get to see a lot of stars, and you would be able to see the Milky Way. Now, the Milky Way is so called because it does look like a stream of milk. And it's called a galaxy because in milk you have the sugar lactose. And lactose is composed of glucose and galactose. So you have galactose, galaxy, okay, kind of associates with each other. So quite incredible. Here's an artist rendition of our Milky Way galaxy. We haven't actually taken a picture of the entire galaxy, otherwise we would be more advanced than we are already. We would have to go very far away and then turn around to take a picture of the galaxy, but we haven't really been that far. We've been very little distance relative to this whole thing. I mean, if you look closely, we have tons and tons of stars, again, about a couple 100 billion stars, like between 100 and 300 billion stars estimated in our Milky Way galaxy alone. And some of the farthest spacecraft that Earth has sent out into space, I believe the farthest being Voyager 1, is just traveling in interstellar space just beyond our own solar system. And then if you just go over to the next star, it has its own solar system, and there's a lot of distance between stars. So we're so incredibly long from reaching that far out to turn around and take a picture of our galaxy. So this is just an artist rendition. In other words, you are here, right here, about 27,000 light years away from the galactic center, which will define light years, I believe, in requirement 4. And here are the different types of galaxies. Here's the spiral, kind of a bit like our own, and Andromeda, but then you have barred, irregular, elliptical, and such. Now this is another artist rendition of what the Andromeda galaxy would look like if somehow we're able to see it. But the Andromeda galaxy is said to be 2.5 million light years away. Now this is also about the same width as our Milky Way galaxy, but it's more dense, meaning it has about 3 or more times the amount of stars, again about 1 trillion stars. But even though it's like light years away, which is the unit of distance, which we'll talk about later, this is how huge it is said to look like. So I remember looking through binoculars after midnight one day in 2015 and finally seeing a part of the Andromeda Galaxy, which is of course named because it's in the Andromeda constellation, which again we'll define constellations later on. So I want to take a little moment, or a brain break if you will, and talk about relative velocities. What does that mean? Well, velocity is kind of a bit like speed, how fast you're going. So Earth rotates at hundreds to over 1,000 miles per hour, depending on where you are on Earth. Here you're going like 0 miles per hour, but over here you're going like over 1,000 miles per hour. And I invite you to do more research to wrap your head around that. But Earth revolves around the Sun at about 67,000 miles per hour. That's about, like 1,000 times faster than on a freeway. Just a little extra, I want to remind you about Kepler's second law, that when the Earth is closest to the Sun, or when any planet is closest to its host star, it's going by faster, and then once it's out here, also known as aphelion, it's going slower. And Kepler's first law that says that the planets go in an elliptical orbit, not a circular orbit, and you can kind of see this is more like an oval, not a circle. The Sun moves relative to other stars at about 43,000 miles per hour. And the Sun orbits the galactic center at about 514,000 miles per hour. Yet, that would take between 225 and 250 million years to go around once. And the Milky Way is heading toward the Andromeda Galaxy at 180,000 miles per hour. So here's the Milky Way, here's Andromeda, and they are actually heading toward each other. Yet that would take about 4 to 4.5 billion years before this happens, if anyone would be here. But this is an artist GIF video or animation rendition of what it would look like. From what I've heard in my studies, no star would actually collide with each other because there is a lot of space between stars. Like looking at this collision several light years away, which is an understatement, it looks like, of course, there's going to be a lot of stars bumping into each other, but in reality, not really. So here's the big takeaway. No matter how still you're sitting right now, you're always moving. And it depends on how fast you want to go. If you're going around the Milky Way, you're going about 514,000 miles per hour right now. If you're just going around the Sun, you're going at about 67,000 miles per hour, all while sitting still on your chair watching this video. So that is our tour of the basics and definitions of astronomy, from meteoroids to galaxies. But there's a ton more out there that you could research if you want. For example, brown dwarf stars, which I kind of hinted at earlier, red dwarf stars, the life cycle of stars in the Hertzsprung-Russell diagram, white dwarfs, which occurs when the life cycle of a low-mass star like our Sun is over and it just shoots out its layers. What's left behind is a white dwarf that is incredibly massive. It's about the size of Earth, but has the density of our Sun, which is very massive. You also have nebulae, which also comes about from a nova of a low-mass star like our Sun. So nebulae refers to cloud or space cloud. So those are like the beautiful images, space images that you see. But that's when all the outer layers of a low-mass star shoots out at the end of its life, leaving behind a white dwarf. You get this beautiful nebula with a white dwarf in the middle. Then there's supernovae. So low-mass stars like our Sun are going to go nova, and then high-mass stars such as Betelgeuse, at the end of their life cycle, when they shoot off all of their layers in this catastrophic explosion, then we call that a supernova. and that could leave behind either a black hole or a neutron star. And the neutron star is one of the most fast rotating objects in the universe that we discovered, and it's blasting off like a lighthouse all these radio waves, and that's how we could record how fast it's rotating. And we call that a pulsar, and some rotate at over 700 times a second, and the slowest rotation recorded is just 4.308 seconds. Neutron stars are incredibly dense. They're about the size of a large city, about 9 to 10 miles, but they're 1.4 times the mass of our sun. So a teaspoon of neutron star material, 1 teaspoon, would weigh 10 million tons, if you could believe that. And again, they're also called pulsars. And then there's quasars, which are the brightest things in the entirety of the universe, and such. But you could research all of that if you want to. It's very incredible. A whole lot more. Okay, requirement 3. Find one interesting fact about each planet in our solar system. Draw a chart or make a display showing their differences in sizes and distance from the sun. So when I taught this in the past, twice in person, I had a printout that I made, and I gave each boy a copy, and this is just an idea. It doesn't have to be exactly like this. If you want, you could press pause and draw this out. What I did is I did some calculations and made some measurements, and then drew all the planets, planets 1, 2, 3, 4, and then the asteroid belt, and then 5, 6, 7, 8, and 9. And this is known as a scale model. That means that if all the planets are lined up exactly like this, and you're so far away that you're able to see the solar system in its entirety like this, then this is what you would see. This is how far each planet would be. So that's what we mean by scale model, which we'll get to toward the end of the requirement. But the sizes I just estimated, planets 1 through 4 are known as the terrestrial planets or Earth-like planets, which we'll get to, and they are significantly smaller yet denser than planets 5 through 8, which are the Jovian planets or Jupiter-like planets, and these are known as the gas giants, and these are significantly bigger but less dense, and we'll get to all of these planets later. What I have down here is a space for you to write the names of all the planets, and how most of them are named after Roman gods, just one after a Greek god, and then their Greek equivalents, the meaning and the mileage from the sun. But there's a whole lot more facts that we're going to go through in each planet, and it depends on what your commander wants. Perhaps your commander wants you to draw something like this and just take 1 or 2 things that we talked about in the planets and just write them down. First of all, what does planet mean? The term planet means wandering star or wanderer in Greek. Why is that? It's because these bright objects that look like stars always moved relative to the more distant stars. So you have constellations such as Orion and Gemini and Taurus and Scorpius, and they're out at the same time of the year, year after year. So I'll clarify that if you're still confused. First, take a look at this image right here. You see the background stars, but then you see some very bright objects, and those are the ones that wander throughout the year, and they don't stay in the same place relative to the background stars, and so the Greeks called them planets or wanderers. So here's an example. Here we have some of the most famous constellations. We have Orion, Gemini, Canis Major is down here, Sirius, the brightest star in the night sky, is in Canis Major, Perseus, etc. Well, let's say that we have a bright star right here, or what looks like a bright star. So when you go out, you make an observation, you draw out all the constellations, and you add this in here as a bright object. Well, in another time of the year or another year altogether, it now might be right here. So how'd that happen? All of the other stars are in the same places. What about this? Well, that's why they call them planets, because these wandered relative to the background stars. So here's an example of one. So here's another example, more of an animation that I took a screen video of. And what you're looking at is due south, and you're seeing all the constellations. And if you notice, the time is 2000 hours, which is 8 p.m. And the date of this particular night is February 1st. So on February 1st, 2010 at 8 p.m., if you were to go out and face due south, this is what you would see. And the purple are either a planet or dwarf planet. Eris is one of the dwarf planets right over here. But when I press play, it's going to go year by year, every February 1st, starting in 2010 at 8 p.m. So the time is going to remain constant. The date is going to remain constant. The only difference is the year. So let's take a look at what happens. Now it's 2011, 2012, 2013, and on it goes. We see Jupiter, we see Uranus, we see Ceres, we see Jupiter again, we see Saturn coming in, we see Neptune. Now notice that the background star stays pretty much exactly the same. It's just these purple dots that don't. And these purple dots are the wanderers, or the planets / dwarf planets. Here's a picture where you have 5 planets in one, picture. What are the 5 planets? Can you point them out? Feel free to press pause. Here's the answer. You see that you have Venus, Jupiter, Saturn, Mars, and Earth down here. Don't forget, Earth is a planet, so you have 5 planets in one shot. So the moon is just a satellite, not a planet. Kind of a trick question. You're facing north here. So this must be evening since this is west. So let's start with the terrestrial planets. Terrestrial means Earth-like, and that's why people say extraterrestrial for any being that lives outside of Earth. Just a little sci-fi fictional stuff. So anyway, these are also known as the inner planets. Collectively, the terrestrial planets are smaller, they're more rocky, and denser. Let's start with Mercury. Mercury is about 36 million miles away from the Sun. Its gravity is 38% that of Earth. So what does that mean? It means that if you weigh 100 pounds on Earth, you would weigh 38% of that on Mercury. Can you calculate that? That's 38 pounds. If something on Earth weighs 200 pounds, it would weigh 76 pounds on Mercury. Therefore, you could jump almost a few times higher on Mercury than on Earth too, because of the gravity. It's named after the Roman god of commerce, travel, and communications. You may have heard of the Mercury dime. A little trivia in numismatics, this is not Mercury, this is Lady Liberty with wings, but people teased about it in 1916 when this coin came out, saying it looks so much like Mercury. I'm sure that y'all know by now this is little g god, this is a mythology, but it was the Romans that somewhat named these planets, except for Earth, of course, after their god, because they were polytheist, so they believed in multiple gods. Again, this is part of mythology, but neat trivia and background story nevertheless. Why do you think they named this planet Mercury? That's because it's closest to the Sun. And again, according to Kepler's third law, the closer you are to the Sun, the faster it orbits around. Well, of course, the Romans, I'm not sure if they figured that out, but they did recognize that the closer a planet is to the Sun, the shorter its year is. It only takes 365 days approximately for Earth to go around the Sun, but it only takes 88 days, Earth days, for Mercury to go around the Sun. But because it seems like it's going around the Sun lickety-split, that's why they named it Mercury after the winged messenger god. And the Greek equivalence to Mercury is Hermes. Mercury doesn't have an atmosphere. That's due to a couple of reasons. One is because it's small with a weak gravity, so it can't hold an atmosphere. 2, it's also because it's closest to the Sun. And because of that, the solar wind literally blows away any atmosphere that tries to form. Also, let's not forget that it's too hot. And when things are hot, molecules move fast, so it's flying out into space faster than it could just stay in one place and develop an atmosphere. So speaking about how hot it is, the day temperature is about 800 degrees Fahrenheit. So you might think the night temperature is just a little bit cooler, right? Actually, no. The night temperature could be negative 280 degrees Fahrenheit. Why so drastically low? Well, that's because Mercury's spin or rotation is very slow. 1 Mercurian day equals 59 Earth days, whereas 1 Mercurian year is 88 Earth days. So Mercurian is basically the adjective describing Mercury, like terrestrial, Earth, Mercurian, Mercury, and we'll be learning some more as we go through the different planets. Therefore, 1 year on Mercury is less than 2 days on Mercury. So if you live on Mercury and you become a 1-year-old on Mercury, you would be less than 2 days old. Now let's go on to Venus. Venus is about 67 million miles away from the Sun. The gravity is 91% that of Earth, which means that if you weigh 100 pounds on Earth, you will weigh 91 pounds on Venus. It's named after the Roman goddess of love and beauty. For a long time, it's been known as our sister planet. It's known as the morning and evening star. And the Greek equivalent to Venus is Aphrodite. What you're seeing now are the clouds around Venus. But if you took the clouds away, this is what Venus would look like. Several decades ago, the Soviet Union, which we'll talk about later in Requirement 8, had sent a bunch of probes around Venus. And a lot of these were named Venera, like Venera 7, Venera 9, for example. And Venera is Russian for Venus. And these were orbiters and landers that were sent from the Soviet Union, which is present-day Russia, around Venus. And some of them were successful and others weren't as successful. But here's a successful one. One of the landers actually landed on Venus and took a few pictures for a couple of hours before it was just consumed by the intense heat and the elements of Venus that it was destroyed. But at least we got some pictures, and this is one of them. Again, it's nicknamed the morning and evening star, and that's because Venus is usually out in the early morning hours or in the evening before it sets in the west. Now, why is that? It's because Venus, along with Mercury, is known as an inferior planet, which means it's closer to the Sun than Earth. And all the other planets, Mars to Neptune, are known as superior planets. But anyway, if you're looking out, let's say this is in the evening, and you see these two planets, well, that's Mercury and Venus. Well, what you don't see are its orbital paths, which is drawn in right here. Why is that significant? Well, let's look at it in a different way. So let's say that the Sun is right here and it's rising in the east. It would be daytime at this point. It's going to set at the west approximately 12 hours later, give or take. Well, the Moon is also going to rise in the east and set in the west, along with the planets. So let's say Mars is rising, and Mars could rise anywhere in the middle of the day or in the middle of the night or the beginning of the night, and it's going to go all across the night sky. Same thing with Jupiter and Saturn. And you'll be able to see the planets go all across the night sky one by one, except for Venus and Mercury. You will never go out at like 9, 10, 11 o'clock at night and see Venus right here, or Mercury, and going all across the sky. Because again, Mercury and Venus are inferior planets. It stays close to the Sun. So let's say that the Sun is right here that I'm outlining. Okay, when the Sun is out, Mercury and Venus are also out at the same time. They won't be opposite from each other, meaning that if the Sun is right here, Mercury and Venus couldn't be observed on the other side of the world. If the Sun is right here, Mercury could be on either side of the Sun, unless it's transiting the Sun or going past the Sun, which is called an occultation. But besides those two occurrences, Mercury is going to be somewhere around the Sun. Same thing with Venus, but at a greater orbit right here. And again, you could see that clearly here. You could see the orbits drawn out right over here. So that's why Mercury and Venus could only be seen in the morning or in the evening. And as the Sun goes across the entire sky during the day, Mercury and Venus are out, but since the Sun is so bright, you can't see Mercury or Venus unless of a total solar eclipse. Here's my picture that I took, I believe, back in 2015, one early morning. And even though I live in the city, this was insanely bright. Very, very, very bright. And this is Venus right here, and Jupiter is right back over here. The temperature on Venus is 867 degrees Fahrenheit, roughly. But if you recall from Mercury, that is approximately just 800 degrees Fahrenheit. How is it that Venus, being millions of miles, tens of millions of miles farther away from the sun than Mercury is, be hotter than Mercury? It's because of the clouds. So remember, these are the clouds of Venus that we see. And the clouds are composed of carbon dioxide gas, which is a greenhouse gas, which traps in the heat inside, making Venus extremely hot. And it rains sulfuric acid as well, which is a deadly poison. And one more thing about the carbon dioxide really reflects the sun's light very brightly. And that's why Venus is the third brightest object in the sky, following the moon, following the sun. So if you see Venus, it's not a UFO, it is a planet. Venus is commonly mistaken to be a UFO since it's incredibly bright, but that's because of the sun reflecting off the carbon dioxide gaseous clouds. So the adjective for Venus is Venusian. So one Venusian day is 243 Earth days, which makes sense. It's past Mercury but before Earth, so it has to be somewhere between 88 and 365. Also, Venus is just a little bit smaller than Earth in terms of size. But get this, one Venusian year equals 224.7 Earth days. Do you see a little problem there? One day is longer than 1 year. So you would be older in terms of days than years if you somehow lived on Venus. Venus is also the only planet that rotates clockwise instead of counterclockwise like the other planets. Going back to Galileo, he discovered the Venusian phases. Hopefully you remember that from Requirement 1 with a brief history of astronomy. And that's because Venus is an inferior planet, so we could make observations of the entire orbit of Venus within 1 Earth year. And when Venus is in front of the sun relative to Earth, we call that a new Venus. And then as Venus continues to revolve around the sun and ends up right here, we see half of it lit and the other half dark. So we call that a quarter Venus. And then you have the gibbous and the full, as well as the crescent. And here are pictures taken over the course of a Venusian year. Well, this looks like half of a Venusian year. Now take a look here. Here's Earth, and here's the new Venus, and here is the crescent Venus. Notice that when Venus is a crescent, it is closer to Earth versus if it was half-lit or a quarter Venus versus a gibbous Venus versus a full Venus. And this sort of shows it. The more full that Venus gets, the smaller it is because it's going around the sun, i.e. further and further away from us. Here's a picture that I took on June 30th, 2015, a date and an event I actually mentioned in my book. I was looking forward to this for like weeks, if not months, about this conjunction between Venus and Jupiter. And here's my telescope, and I got to see both Venus and Jupiter in my eyepiece. This is just a picture that doesn't do its justice, but it was incredible nonetheless. They said this was like the first time in 2,000 years that Venus and Jupiter were that close together. Again, that's called a conjunction. Okay, now Earth. Earth is about 93 million miles away from the sun, between 91 and 95 million miles. It's actually closer to the sun in the winter time, around January 3rd or 4th, which if you saw earlier, that would be called perihelion. And when Earth is furthest from the sun, that's aphelion, and that's actually summer around July 3rd or 4th. So I just want to dispel the myth that the closer Earth is to the sun, the more closer to summer it is. It's actually the opposite. Earth has one moon, and it's the first planet that we've seen that has a moon. Mercury and Venus do not. It's the only planet to support life. So one solar day is 24 hours. So imagine going outside and enjoying this nice panoramic view, and then the sun rises in the east and then is now high in the sky, which means that you're facing due south at this point. Okay, for the sun to go all the way around again and land at this exact spot right here takes precisely 24 hours. Alright, well, one sidereal day is 23 hours, 56 minutes, and 4.0916 seconds. What? Well, a sidereal day refers to a day relative to the background stars. The solar day is relative to our sun. So remember that when the sun goes around the Earth, well, it's really the Earth rotating, but it looks like the sun's going around the Earth. That takes 24 hours for it to get to the same position in the sky. However, when we refer to the sidereal day, that's actually the complete rotation of the Earth. And I have a graphic to show this here in a few seconds. But let's imagine that we're in our beautiful scenic panoramic view right here again, and we're facing south. And recall that before the sun was right here. Okay, now the sun is going to land right over there. See the difference? Okay, this is after one complete rotation of Earth, or 23.9 hours. It's going to take that little bit of time for the sun to get back to where it was before. Now, how does this work? Well, here's Earth, the blue circle, and here's Earth at position 1, position 2, and position 3 as it goes counterclockwise around the sun. Now, at position 1, let's say that you're standing right here, and you're facing the sun, directly at the sun. Well, from position 1 to position 2 is exactly one rotation of Earth. So you're facing the same exact direction. These are both parallel lines, and as you could see, if you're standing right here, you have to look this way to see the sun. That would be the sun right over here. But it takes a very, very small fraction of a day, just a few minutes, for it to go from position 2 to position 3, and now you're directly facing the sun. Because again, in position 2, you're not facing the sun. In position 3, you are. And this scenario over here would be you at position 3 facing the sun. Now, how does this happen? Well, you got to remember, even though the Earth is going counterclockwise around the entire sun, at the same exact time the Earth is rotating about its axis. So after one complete rotation, you're going to be facing the same direction. Okay, from position 1 to position 2 is one complete rotation, but you see you're not facing directly at the sun, it's just off to the side. You have to wait till position 3 until you are facing the sun, because from position 2 to position 3 it rotated just a little bit. And this is all due to the fact that not only are we going around the sun, but at the same time we're rotating, and that's what creates these two main days, solar and sidereal. Now, 1 year equals 365.24219 days, which is almost a quarter, 0.25. So every year we count 365 days and then start the next year, but we have a quarter day that we didn't spend. So after 4 years, we saved up 4 quarters of a day, and now we could spend it for an extra day, and we call that February 29th, and that's the leap year. I do have a YouTube video explaining this in more thorough detail if you're interested, that I filmed on February 29th, 2020, and I'll link it in the card if you're interested in the YouTube video. But that's the origin of the leap year. It's because a year isn't exactly 365 days. Okay, now on to Mars, the red planet. Mars is about 141.5 million miles away from the Sun. The gravity is the same as that of Mercury, 38%, which also means you could jump about 3 times higher on Mars than on Earth. Now let's see if we could understand why they named it Mars. Whether you see it with the unaided eye or a picture or through the telescope, it looks red. And so red could be, like Valentine's Day, meaning hearts and love. But we already have the planet named after the goddess of love, and so we have to think of another name. What else is associated with red? Blood, carnage, war. So Mars was the Roman god of war, and the Greek equivalence is Ares. 1 year on Mars is 687 Earth days, which is approximately 1.88 Earth years. So 1 year on Mars is just under 2 years on Earth. But going back to the color red, why is it really red? Well, think about the oxidation of iron. Okay, what happens when iron is exposed to oxygen and moisture? Well, it turns into rust. Well, what's on Mars? Mars has a lot of iron in its rocks, but what else do you need again? You need oxidation, meaning you need oxygen. And yes, indeed, Mars does have a fraction of oxygen in its atmosphere. On Earth, it's 21% oxygen, 78% nitrogen, but on Mars, there's just like a trace amount of oxygen. The majority of the Martian atmosphere is carbon dioxide, and Martian is the adjective of Mars. Okay, so we have iron, we have oxygen, but what about water? There's also amounts of H2O as well throughout Mars. Iron is also the reason why blood is red. Here's my drawing from anatomy class of the human heart. Blood pours into the heart, goes to the lungs to receive the oxygen, goes back into the heart and circulates throughout the body, delivering oxygen. Inside the blood, you have all of these proteins, and inside the protein known as hemoglobin, you have 4 specific molecules called heme, and in the middle of it, you have iron. So that's why it's important to eat a lot of iron-rich food so that your blood could contain enough iron to pick up the oxygen. Without it, you might go into iron deficiency anemia, which is not really good. So our blood is red because of iron, and Mars is red because of iron. Okay, so the deepest canyon in the solar system is found on Mars. It's about 4.3 miles deep, and it's called Valles Marineris, also known as Mariner Valley. It spans over the entirety of the contiguous United States. That's how wide it is. The largest volcano in the solar system is also found in Mars. Now this is very interesting. It's called the Olympus Mons, and is almost 2.5 times bigger than Mount Everest. And it could cover nearly the entire state of Arizona. So a lot of astronomers have sent rovers and other probes to Mars to examine its surface. In fact, I remember being in either first or second grade when Spirit and Opportunity were named and then subsequently sent over there to examine the Martian surface and to take pictures. And fairly recently, as of filming this, NASA's Jet Propulsion Laboratory just sent the Perseverance rover and Ingenuity helicopter to Mars, and it launched on January 30th, 2020 at Cape Canaveral Space Force Station in Florida, and it landed in early 2021. In fact, the top right picture that you see is the first photo on Mars by Perseverance. And the 2 lower pictures are animations, computer animations of the Perseverance rover, what it looks like, and the Ingenuity helicopter. Now, about the Ingenuity helicopter, this aircraft became the first power-controlled flight on another planet other than Earth. So what's a little bit interesting in my outpost, I was teaching this on Zoom, the 3rd time I was teaching astronomy, first time on Zoom when this was happening, and I was getting these slides ready around the same time. So I added it in and told it to the boys at my outpost. Here are the 2 moons of Mars. So Mars has 2 moons, Phobos and Deimos, which are named after the 2 sons of Ares in Greek mythology, because Ares is the equivalent to Mars. Phobos and Deimos means fear and dread, respectively. So phobia means fear, Phobos. So, and these obviously are potato-shaped. It's theorized that 2 asteroids got caught in Mars's gravity and started to orbit it, and that's how Mars got 2 moons. Since these 2 probable asteroids in the past are now orbiting Mars, we call those the natural satellites or moons of Mars. Okay, now onto the Jovian planets. So Jovian is actually the adjective for Jupiter. Jovian means Jupiter-like, and they're also known as the outer planets. So these are significantly bigger but less dense. They're known as the gas giants because they're mostly gas. In theory, you could fly right through them because there's no surface. Again, it is theorized that there's a rocky metal core at the center. However, I don't think it's possible to go through it unless you have some out of this universe, literally spacecraft, because of the intense density within these. There has been a spacecraft that deliberately plunged into Jupiter a while ago, and it only lasted just a little bit inside before the density was so huge that it was literally crushed. So we'll be going through these one by one, and wait till you hear about the density of Saturn. But first, here's a quick question. As we're going further out from the sun, are the planets revolving faster or slower? And remember, to revolve means to orbit around the sun. Press pause if you need to. Hint, think of Kepler's third law. The answer is that they're moving slower and slower and slower and slower around the sun. Okay, Jupiter, the largest planet of the solar system. This is about 483 million miles away from the sun. It orbits once every 12 Earth years and has the fastest day of under 10 Earth hours. Or, the fastest rotation speed, about 10 Earth hours. Okay, the gravity is approximately 240% that of Earth. An object that weighs 100 pounds would weigh 240 pounds if, in theory, they were able to stand on Jupiter. Jupiter is mostly hydrogen with 17% helium and just a trace amount of water. You can easily tell that one of the things that make Jupiter famous are the bands. You could see the dark and light colored bands, and the reason why there's bands are because of the alternation of rising and falling air. As you see the dark red and brown bands, those are typically falling air, and those are called belts, and they are probably composed of a chemical called ammonium hydrosulfide. The white colored bands that you see are called zones, and they're typically rising air, and those are tops of a cloud that's composed of a smaller molecule, therefore less dense, called ammonia. And in 1994, there was a comet named Shoemaker-Levy that had broken up into 21 pieces and plunged into Jupiter. This was world-renowned. This happened about a year before I was born. I believe my grandfather remembers this. And this was like the first time that scientists had got to see objects actually plunge into another planet like this. So this was big news back in 1994. It was named after the Roman chief god, the god of the sky, lightning, and thunder, and the Greek equivalent is Zeus. With a 3.1 degree tilt, Jupiter experiences no seasons. Earth has seasons because it's tilted about 23.4 degrees on its axis. If you take a look here, about 3.5 moons put side by side spans the diameter of the Earth. Well, 11 Earths put side by side could fit across the diameter of Jupiter. 10 Jupiters could fit across the Sun. And here are the size comparisons. This is how huge the Sun is compared to Jupiter, compared to Earth, compared to that little dot right there, which is the Moon. Now, I bet that you could use simple arithmetic to find out if you have a lot of Earths put side by side together, how many Earths can span across the diameter of the Sun. Well, that would be 11 times 10, because 11 Earths could fit across Jupiter, and 10 Jupiters could fit across the Sun. So about 110 Earths put side by side. And you could do this on your own if you want to, but how many moons could span across Jupiter and the Sun? Just some fun with mathematics. Here's the Great Red Spot. The Great Red Spot is like this powerful hurricane windstorm. It could go about 270 to 425 miles per hour. The Great Red Spot had been discovered centuries ago, but has had a lot of observations in the past several decades. If you look at these three images from 1995 to 2014, it is actually shrinking. About 2 to 3 Earths can fit inside the Great Red Spot, and over 1,300 Earths can fit inside Jupiter. If you look up the volume of Jupiter and you divide it by the volume of the Earth, that's how you could find out how many Earths could fit inside Jupiter, and you could do the same thing with the Sun. How many Jupiters can fit inside the Sun? And again, that's by taking the volume of the larger object and dividing it by the volume of the smaller object. Okay, Jupiter has many, many moons, but there's 4 big ones, and that's Io, Europa, Ganymede, and Callisto. I believe that I pointed these out accurately because this is the order of increasing distance from Jupiter. In other words, Io is the closest to Jupiter, followed by Europa, then Ganymede, and Callisto. And these were named after the lovers of Zeus, the Greek equivalents to Jupiter in Greek mythology, just for some trivia. And these are the 4 stars, quote-unquote, that Galileo discovered through his telescope, but determined that these are actual satellites orbiting another planet. And if you look through binoculars or a small telescope, you'll definitely see these, and they're incredible to look at in person. That and the rings of Saturn. Now, let's focus on Ganymede for a second. Ganymede is the largest satellite of the solar system, and it's actually bigger than a planet, the planet Mercury. Io actually has active volcanoes. You could see some geysers. And it's theorized that Europa has a subsurface ocean, or below the surface there's an ocean, scientists theorize. And here are close-ups of the 4 moons, Io, Europa, Ganymede, and Callisto. I don't know, I think Callisto's the most neat-looking satellite. Here's my picture of the Jupiter-Saturn conjunction on December 21st, 2020, through my semi-professional camera, not really professional, but you could see the rings on Saturn here. There were the moons visible, but not in this picture. But I do have a YouTube video if you're interested in that. Here's another picture of Jupiter with a few of the moons, and you could see the shadow that the moon cast on Jupiter. And this is the south pole, I'm sure, of Jupiter. Here's the Great Red Spot. So this is looking at Jupiter at a different angle. Okay, now let's move on to Saturn. Saturn, I will tell you now, is my favorite planet. But if yours is Jupiter or Earth, and of course that's okay, or any other planet, but I'm just saying this is my favorite. I could watch it through a telescope all night long. Saturn is 887 million miles from the Sun, on average. It orbits once every 29 Earth years. So, for example, if I were to have grown up on Saturn, I wouldn't be a year old. Now, for those of you who don't know, why is it called Saturn? Well, if you look at Saturn with the unaided eye, or even pictures, or even this picture right here, you can notice that it's kind of a bit yellow-orange. That might remind you of wheat fields, okay? Agriculture. So Saturn was the god of agriculture in Roman mythology. And the Greek equivalent is Kronos, or Cronus, kind of it where we get the prefix for time. And it said that Saturn was the keeper of time. So you have like chronology, chronicles, chronological, and such. So just some etymology there. So again, Saturn was the Roman god of agriculture and harvest. When I was teaching this for the 3rd time, there was a boy in my outpost that knew all about the Roman and Greek gods and such, and why the planets were named, so I thought that was neat. The density of Saturn is 0.71 grams per cubic centimeter. Now this is the lowest density of any planet, and the only planet with a density less than 1. Well, water has a density of 1. Anything greater than 1 will sink, anything less than 1 will float. So do you know what that means? It means that if you have some galactic size, maybe not that big, but if you have a solar system size ocean and put Saturn in it, in theory it would float. All the terrestrial planets, of course, would be down on the bottom, but this is just, I guess, for theoretical astronomers. Here is one of my favorite pictures of Saturn. This is the other side of Saturn with the sun behind it. You can see a little bit shining over here. Here's another picture where Saturn is in front of the sun, and you see Earth and the Moon here, you see Venus, and you see Mars. And here's more pictures of Saturn that I like, that are very neat, and here's Earth right here. I've heard that they try to get everyone on Earth to look up at the sky and smile for the picture, but anyway. Okay, now let's talk about the most famous part of Saturn, which are the rings. And the rings are composed of chunks of rock and ice of various sizes. So if you look up close, this is actually what the rings are composed of. And unlike the asteroid belt, these are actually close together, and in a sci-fi space invaders game, whatever, you would be dodging these chunks of rock and ice. Remember, asteroids aren't this close together in real life, but the rings of Saturn, for example, are. This is an artist's depiction of what it might look like flying above Saturn with its rings here. And another artist's depiction, what if Saturn replaces the Moon? Well, I believe if I'd done the math correctly, the rings would not fit. It would collide with Earth, but just imagine. There is a video, like a daytime video and a nighttime video on YouTube that I watched. What if the Moon was replaced by all the planets and such, and what would it look like? So Saturn has tons and tons of moons, just like Jupiter, but Titan is very highly studied. It's the largest satellite of Saturn. It's the only one known so far to have a substantial atmosphere. The atmosphere has mostly nitrogen, along with traces of methane, which is a hydrocarbon. And it is said to have rivers, lakes, and oceans, but not of water, but of liquid hydrocarbons, such as methane and I believe ethane. Okay, now on to Uranus. Uranus is 1.784 billion miles away from the Sun. It orbits once every 84 years. It's completely on its side. How do we know that? It's because of the rings. Uranus has rings? Yes, Jupiter does too. Same thing with Neptune. Here's actually the pictures of the rings of Jupiter, Saturn, Uranus, and Neptune. But we only see Saturn most prominently, but indeed the other three have rings. And Jupiter, remember, it's about a 3.1 degree tilt. The rings being horizontal tells us that Jupiter is almost right side up, which means that it doesn't have seasons, as we talked about. Saturn would have seasons because it is tilted. So here's the $1.784 billion theoretical question of the requirement. If, for whatever reason, you were physically able to live on Uranus, in what season do you want to be born? Because you're going to live in that season for about 21 years. So taking a look at this diagram here, on the left side, you have the southern summer solstice, and that's because the South Pole is toward the Sun. And on the opposite side, the North Pole is toward the Sun. But because it rotates on its axis like that, either pole is going to either be toward the Sun or away from the Sun for about 21 years. And then the equinoxes that happened in 1965 and 2007, the sides are facing the Sun. But the whole point here, looking at the left side at the southern summer solstice again, that hemisphere is going to be facing the Sun for a couple of decades, and the other side is going to be nighttime. But, you know, the Sun looks very small all the way over there anyway, but it's just something fun to think about. The seasons of Neptune are even more long because it's a bigger orbit, as we'll talk about next after this planet. And in lieu of orbiting the Sun once every 84 years, Neptune orbits the Sun once every 165 years, so each of the 4 seasons are just a little over 40 years each. But Neptune would experience 4 seasons since its tilt isn't that drastic. Uranus was discovered by William Herschel in 1781, and the first planet identified with a telescope. Because Uranus is so far away, along with Neptune, it just looks like another star. So more distant planets are harder to identify and easier to mistake for stars. It's the only planet named after a Greek god, the god of the heavens and sky. Why do you think that is? Well, the color of Uranus could remind you of sky blue, right? It looks like the sky, the heavens, right? So that's why they named it Uranus. Not only that, but Uranus was the father of Kronos, who was the father of Zeus. The Roman counterpart is Caelus, I believe that's how you pronounce it. And Caelus was the father of Saturn, who was the father of Jupiter. Another interesting fact is that Jupiter was the father of Mercury and Mars, and Zeus was the father of Hermes and Ares along with Aphrodite. Saturn was also the father of Neptune and Pluto. Just somewhat interesting to know. You'll probably learn mythology in school and get to raise your hand and say, oh, I know this. But just remember, and I'm sure you do, this is a little g god, this is just mythology. Okay, the largest moon is Titania. Uranus and Neptune also have tons and tons of satellites orbiting it. I don't think as many as Jupiter and Saturn, but they might be still counting. The numbers fluctuate from source to source. Finally, onto Neptune. Now, if Saturn didn't exist, Neptune would probably be my next favorite planet because I just love blue, and this is a very beautiful hue of blue. Neptune is 2.79 billion miles away from the Sun. It orbits once every 165 years. Therefore, it's probably safe to say that no one would be able to turn a year old on Neptune. It was discovered in 1846. Asterisk. Okay, why did I put that asterisk? Was it really discovered in 1846? Well, let me show you this. This is Galileo's notes right here from over 400 years ago. If you notice, he put Jupiter right here, and he was drawing in the satellites here. But then he made a dashed line to this right here, and just made a note of this. Well, what's neat about computers is that you could go back in time and find out what the night sky looked like. And this is it. So a person went back in time to the date that Galileo made this, or made this observation, and zoomed in on where Jupiter was at. And if you notice, everything lines up. Here's Jupiter, here's Europa and Callisto, exactly where it's at right here. Here's Ganymede, so we got the right date. But take a look here. This is where Neptune was that night. So Galileo probably discovered Neptune. And people are like, okay, maybe that's a lucky guess. Maybe he saw something else. Well, here's another observation that he made at a different date. Here's Jupiter and a couple of the moons. And then he pointed this out right here with a dashed line. And this is what the night sky looked like that night. And if you take a look, here's Jupiter, here's Europa, Callisto, and take a look right over here where Neptune was that night. Like, pretty much the same angle right here. So I really think it's safe to say that Galileo was the person who discovered Neptune. Okay, so why did they name it Neptune? Well, the hue of the blue probably reminds you of the ocean, right? The ocean, water, seas. And Neptune was the Roman god of the sea. The Greek equivalent is Poseidon. It is the coldest planet, which should make sense. It's the furthest from the Sun, about -300 to -400 degrees Fahrenheit. And it's the windiest place in the solar system, especially the Great Dark Spot, which keeps on disappearing and reappearing. Maybe not the same one, but this has been studied for at least decades. Again, it's the windiest planet, between 45 miles per hour to approximately 1,300 miles per hour. Why are Uranus and Neptune both blue? Well, it's because of the methane, or CH3, in the atmosphere. Methane is a hydrocarbon. And if you remember when we briefly talked about Edwin Hubble, light travels in waves, and a little piece of it are the colors of the rainbow. Red, orange, yellow, green, blue, violet. Well, light has all the colors plus all the invisible light that we can't see, the radio waves, gamma rays, X-rays, and all that stuff. Well, that light that comes from the sun travels all throughout the solar system, and once it reaches Uranus and Neptune, the light runs into the atmosphere and the clouds around Uranus and Neptune. Now, according to this diagram, the methane gas absorbs the red light and transmits the blue light. That means the red light just gets absorbed here, and then the blue light goes through, which is what transmit means, it goes through. However, when the light reaches the methane clouds, it bounces off or reflects back into space. We see color because it's reflected off. It absorbs all the other colors, but it reflects that color. So if you're seeing a red object, it's absorbing orange, yellow, green, blue, violet, but it's reflecting red and enters our eyes and we see it as red. Well, blue light is reflected off the methane clouds, goes back into space, reaches Earth and our eyes, or the cameras of the space probes taking pictures, and we see it as blue. The largest moon of Neptune is Triton. So the largest moons of Saturn, Uranus, and Neptune are Titan, Titania, and Triton respectively. And finally, to give an honorable mention to the next planet, Pluto. Oh no, not that Pluto. This Pluto. So Pluto is a dwarf planet. It was discovered in 1930 but demoted on August 24, 2006 by the International Astronomical Union. This was right before I entered grade 6, and I will never, ever, ever forget when this happened. So when I was born, there were 9 planets. Technically a little joke there. Anyway, so Pluto is neither terrestrial nor Jovian. Rather, again, it's a dwarf planet because it doesn't fit the definition of a planet. There's 3 criteria for a planet. It must orbit the sun, and it must be round, and Pluto checks that. However, it must clear its orbital path, in which Pluto doesn't. It actually crosses the path of Neptune. But a lot of people say, well, does that mean Neptune's a dwarf planet? And I'll just leave it at that. Let's move on. Pluto was named after the Roman god of the underworld. The Greek equivalent is Hades. And it's 3.67 billion miles away from the sun. I also remember in, I believe it was July 2015, when the space probe made it to Pluto and took this picture. And it was like the first picture ever taken of Pluto this close and this clear. So I remembered when that made the news. It orbits once every 248 Earth years. And it's located in the Kuiper Belt region. So here's the Sun, Jupiter, Saturn, Uranus, and Neptune. The orbital plane of Pluto is actually tilted. Here it's relatively flat, but Pluto, it's tilted a bit. And remember, the Kuiper Belt is so far away from the Sun that you have a lot of ice, and that's where comets come from. And the comets orbit the sun and sometimes get pulled in, and then they develop a tail and then pass by. Here's another picture, probably an earlier picture, of Pluto and Charon. Charon is one of the satellites of Pluto. And here's some more dwarf planets. You have Pluto, you have Eris. I believe I remember when Eris was discovered, January 5th, 2005, I believe that made the news as a potential 10th planet. I was so excited. But then it was just a dwarf planet. Ceres, which is the largest asteroid and a dwarf planet in the asteroid belt. Haumea, Makemake, you also have Cetina. All of these, except for Ceres, would be in the Kuiper Belt region. And here's Mercury for a size comparison. And here are the orbits of the different planets, dwarf planets that is, relative to Neptune and the rest of the solar system. This is very neat. It's in Washington, D.C. I haven't been here, but I've heard about it. I would hope to be here one day. But it's a scale model, and it's exactly what I was talking about in the beginning of the requirement when I made that diagram, where the entire solar system is downsized to scale, such that 1 foot equals this many miles in real life. And now it's your turn to make a scale model. So if you want to, and you could show your outpost, you take a piece of rope, and you'll need about 35 inches. Mercury would be 4 inches from one of the ends. So take your working end, and then 4 inches, you could put a knot, you could put a stripe, you could put a bead anywhere, and make sure it stays in place. Venus would be 7.5 inches. Earth would be 10 1/3. Mars would be 15 3/4. Jupiter would be 4.5 feet. Saturn would be 8 1/4. Uranus would be 16.5. Neptune would be 26 feet. And if you want to add Pluto, 34 feet. Now once you put all of this together in one piece of rope, this would be a 1 to 570 billion scale model. That means that the distance is really 570 billion times larger than what it is. So this means that for every 1 inch of your rope, that's representing 570 billion inches, which is about 9 million miles in real life. There are other ways to make a scale model. You could make a scale model with sizes too. I'm sure you could go online and find the materials. For example, a basketball would be Jupiter, Saturn would be a soccer ball, and for the terrestrial planets you will probably use smaller objects like an M&M, a grape, etc. So here are some pictures of planets seen in the daytime, which I think are neat. And so that was our tour of all the planets from Mercury to Neptune, and an honorable mention to Pluto at the end. Let's now move on to requirement 4. Explain what is meant by light year, give the distance in light years to the nearest star, and the estimated distance to the farthest galaxy. If you turn on a light switch, it comes on, but it's not instantaneous. It seems like as soon as you turn on the light switch, it comes on. As soon as you turn on the light switch and complete the circuit, electrons start to flow. That creates electricity. From the light bulb to your eyes, it again seems to be instantaneous, but no, the light is propagating or moving through space, and it moves from the light bulb to your eyes, and it takes time to do that. The speed of light is the speed at which light travels. Light travels at 186,282 miles per second. So every single second, that's how far light travels. That's about 10 million times faster than on a freeway. The speed of light is so fast that it can go around the circumference of the Earth at the equator 7.5 times per second at the surface. So what is a light year? Well, that's the distance that light travels in 1 year. Let me dismantle a misconception. A light year is a unit of distance, not time. Think about it. If you said, oh, this homework is going to take me 10 million light years for me to finish, well, you just gave a unit of distance, not time. In other words, it's like saying, boy, this homework is going to take me 60 miles to finish, or 100 miles to finish, or 1,000, which doesn't make sense because you're using a unit of distance to describe how long it's going to take, or how long you think it's going to take to finish your homework. So again, a light year is a unit of distance, and it's the distance that light travels in 1 year, which equals roughly 6 trillion miles, or 9.5 trillion kilometers, which is very far. There's also another unit that isn't part of the merit, but I just wanted to add, especially if you get into astronomy or astrophysics. It's called the AU. Now that stands for astronomical unit, and that's just the average distance between the sun and the earth, and we set that standard and we just call that the AU, or the astronomical unit. Mars is 1.5 AU from the sun, which means that Mars lies 1.5 times farther from the sun than Earth is. Saturn is approximately 9.5 AU, and Neptune is approximately 30 AU from the sun. So going to Neptune, what that means is that Neptune is 30 times farther from the sun than Earth is. That's all what it's saying. And 1 light year is approximately 63,240 AU, or astronomical units. Now, are you ready to travel to the moon at the speed of light? Watch closely. So how was it? Indeed, the moon is about 1 light second, which means that every time that we see the moon, we are seeing 1 second in the past, technically. When we look at the moon and the stars, and our own sun, the light traveled through space and entered our eyes. That's how we see it. But it took time for the light to enter our eyes. In the case of the moon, it was 1 second. But in the case of most of the stars, it could be decades or even centuries or millennia before it reaches Earth. Now, the merit asks is how far is the nearest star? They probably meant the nearest star other than the sun. But I'll go ahead and say that our sun is about 8.5 light minutes or 500 light seconds away, which means that the light from the sun that we receive took about 8.5 minutes for it to propagate through space in order to reach our eyes. The nearest star other than the sun is Proxima Centauri, which is on your screen, and it is approximately 4.243 light years, or approximately like 25 trillion miles, give or take. Again, the light traveled for 4.2 years approximately for it to reach our eyes. So every time that we see the star, we are literally looking 4.25 years in the past. Sirius, the brightest star in the night sky in Canis Major, is 8.6 light years away, which means that it took 8.6 years for it to reach us. If you happen to be 8 years old, which is a 20 to 25% possibility since you're in Discovery Rangers, then you will be looking at a star around the time that you were born. So I don't know, to me that's neat. And then there's some stars that are thousands of light years away, which means that you're seeing stars at the time that Jesus lived, at the time that Abraham, Isaac, Jacob lived, at the time Noah lived, and that's also neat to think about. The nearest known galaxy, and I emailed a couple of astronomers to try and ask them, is this up to date? Like, is this the farthest known galaxy? Because at any time they could discover an even farther galaxy. Well, anyway, this is SPT 0615JD, which is said to be 13.3 billion light years away, and the observable horizon of the universe is approximately 13.8 billion light years away, which is almost at the edge. So the observable horizon is basically the farthest out that we could possibly see. Is about 13.8 billion light years away. Now, remember, this is not a unit of time, it's a unit of distance, and that's how far out we could see. I also just want to add the largest known galaxy, since we're kind of been talking about galaxies. This is IC 1101, which is a supergiant elliptical galaxy. It's approximately 1 billion light years away. Now, just for some size comparison, here is our Milky Way. Our Milky Way is approximately 100,000 light years across, but this one is about 2 million light years across. And again, our Milky Way is only 100,000 light years in diameter. Okay, requirement 5. Explain the difference between an asterism and a constellation. Here are all the constellations that we have. There are 88 of them. You see the ones in gray are known as the zodiacal constellations. And all that means is that these lie on the ecliptic, which is right here. What is the ecliptic? Well, remember that the sun rises in the east, goes all the way across the sky, and sets in the west. And it's going to follow that line or that arc all across the sky every day. You'll never see one day the sun rise in the southeast or the northeast or north or anything. It's always going to be from east to west. Well, all of these specific constellations, 13 of them technically because of this one right here, also lie on the ecliptic. And we'll get back to this later. So I'm going to go ahead and define constellation here and then show you the definition for a review. Constellations are basically boundaries drawn out in space, like this, kind of bit like states in a country. That's all what a constellation is, and this includes all the stars, as well as all the nebulae and all the superclusters and other clusters, star clusters, open and closed star clusters, galaxies and such. Those are all included in a constellation. For example, Virgo isn't just the main stars that make up the pattern. but all the other stars, along with anything else found within this boundary or this region right here that astronomers divided up here, including what they call the Virgo supercluster. You also have Orion right here, and inside Orion you have the Orion Nebula, as well as the Andromeda galaxy inside Andromeda, which is why they named that galaxy after it, because it was inside the constellation. But the more common definition of a constellation are stars that make up a pattern, and they're either based on what they look like or of man's imagination, and from it stories were developed. For instance, in Taurus you have the Pleiades, which I showed you earlier. It's an open cluster, and the Pleiades represent the seven sisters, and as the mythological story goes, Orion the Hunter chasing after the seven sisters. There's a bright star in Taurus called Aldebaran, and Aldebaran is Arabic for follower, and as you see the stars move from east to west in the night, Aldebaran looks like as if it's following the Pleiades, or the seven sisters, all night long. And according to mythology, Scorpius the scorpion stung Orion, and both were placed up in the stars. So if you could make believe these constellations moving toward the right, then Scorpius is also moving toward the right or toward Orion. So technically, as the story goes, Scorpius is chasing Orion. Now, Orion and all these constellations by it are winter constellations, which means that they're typically out during the winter time, and then Scorpius is a summer constellation along with these. So Orion and Scorpius can never be seen in the same night sky at the same time. And according to the story, Orion the Hunter is running away from Scorpius that stung him. Just some more mythology, I guess. Anyway, the constellations, the pattern of the stars, that is, some of them look like what they depict. For example, if you look at Scorpius, it actually looks like a scorpion. But others, again, you have to use your imagination. Constellations usually depict people, half person, half animal, like Centaurus. They could represent objects like Sagitta, which is an arrow. And again, there's a constellation about a woman's hair, and that is Coma Berenices. And animals like Leo the lion, Ursa Major the big bear, Ursa Minor the little bear, Canis Major the big dog, Canis Minor the little dog, Monoceros, which I believe is a unicorn, and etc. So here's the definition of a constellation. It is an entire group of stars within its boundary, including nebulae, galaxies, etc. Also, a group of stars forming a pattern in its boundary. That's also a constellation. Now, an asterism is a prominent group of stars that are part of a constellation and form a more brilliant, recognizable pattern. However, they aren't official. Constellations are official and is observed by scientists, astronomers, astrophysicists, but an asterism is kind of like a layman's guide of the stars, and to just quickly point out some of the bright patterns, which may or may not be the actual picture of the constellation, which we'll get to. So you go out in the night sky and you see a group of stars, then you connect the dots, and then form an image in your mind. So this is Leo the lion, and again, that is due to just seeing these stars and using your imagination. Here's another one. This is Sagittarius, and these are the stars forming the main pattern of Sagittarius. But I want you to take a look at the golden lines right here. If you were to take away the thin lines and take them all away and just see the bold lines, what does that look like? Well, that would look like a teapot. But a teapot, that's not official, but if you go out in the night sky, you could easily see this because it's brilliant, which means it's bright, and therefore that is an asterism. Here's another one. You've probably seen the Big Dipper, right? Well, the Big Dipper is not a constellation. Ursa Major is. There's a lot more stars to Ursa Major than just the Big Dipper. The Big Dipper is just an asterism. Here's Hercules, and you have the keystone asterism in the middle. And then you have the Hercules cluster, named because it was in the Hercules constellation. Of course, not every cluster, nebulae, or galaxy found in constellations are named after the constellations, but some are. For example, the Ring Nebula is in a constellation that's not named Ring. Here's Pegasus, and right here you have the baseball diamond asterism. So people look to constellations to let them know what season they're in. Leo Major signified spring, Scorpio signified summer, Pegasus signified autumn, and Orion signified winter. Again, Orion and Scorpius will never be seen in the same night sky. So what you see in the sky depends on the time of the year. So if you take a look, you have the sun in the middle, you have the earth going counterclockwise around the sun, and then you have the zodiacal constellations over here. Well, let's say it's August 21st, and it's nighttime, so you're facing this way. What do you see rising in the east, going all across the sky and setting in the west? Aquarius. Let's say it's November 21st, and it's nighttime, and you're looking at Taurus. Well, if you take a look at the golden circles all around, that represents the sun. And then what are these dates about? Well, if it's August 21st and it's daytime, and you look toward the sun, which zodiacal constellation is the sun in? Well, it is in Leo, over here by this star. This star is called Regulus, just for some trivia, but remember it's around here. And this is the sun's apparent position in the zodiac, and this is where, all the signs, what's your sign and come from, this is where it comes from. So, like Cancer's in July to August, Leo is from August to September and such. But I do have another picture to help make the point. So let's say it's August 21st, and you're looking toward the sun. The sun should be in Leo somewhere, right? Well, let's go to that computer program again, although I think this is a different one. But you just put in the date, and you put in the time, and it's noon, and where's the sun? It's right in Leo by the star Regulus. So remember, the ecliptic is the line across the sky in which the sun travels through, and all the other constellations in the zodiac. And month after month, the sun is going to appear in a different sign, quote unquote. Like the month previous, it was in Cancer. 2 months previous, it was in Gemini. And towards September, it would be over here by Virgo. So again, this is in the middle of the day. You're not able to see any of these stars or constellations in daylight, but this is where such constellations are on August 21st at noon. Here's a video, or screen video that I took. And in this video, the Earth is facing toward the sun, so it's daylight, and the constellations behind it. So the top screen is the view from Earth. Now it's opposite. Now it's nighttime, and you're facing away from the sun toward the constellations. That's what you would see. Okay, so this is a very famous constellation. You probably know the name. It's Orion. You have the famous Orion's belt. Orion's nebula is over here. You have Betelgeuse and Rigel, which are two giant stars. You also have Saiph, Maesa, and Bellatrix for star names. These have names too, but I forgot. But the point is when you look at the stars, do you think the stars in the constellation are right there in the same spot? Well, no. The stars are actually at different distances away. So if you were to go around the constellation Orion, you would see all the stars in different places, in different positions. But in our perspective, it looks like this familiar pattern. But if you were on an exoplanet somewhere in these background stars, it would look totally different. And online, YouTube specifically, there's like a video that you could watch that is like a 3D tour of the constellations. Here's just one of them, and this is the Big Dipper. It's an asterism, actually. And this is what would happen if you were to fly around the Big Dipper. In our perspective, the stars look like they're right next to each other, making this pattern, but they're at different distances away. So this part might be good for commanders who are watching and considering teaching this merit in person. As I taught this a few times in the past, I used a little object lesson about why some constellations are seen at one part of the year and at another part of the year they're not seen. I used a whiteboard to represent the sun. I took a couple of the boys on one side of the whiteboard to represent the winter constellations like Orion and Gemini and Taurus, and I took a couple of other boys on the other side of the whiteboard to represent the summer constellations, such as Sagittarius and Scorpius. And then I took the remaining boy or boys and I had them revolve around the whiteboard. And for example, on one side, the two boys that represented the summer constellations were seen. And so then the boy made a half turn or an about face and faced the whiteboard, and I called out to the boys representing the winter constellation. You knew that they were behind the whiteboard, but you couldn't see it. That's because the sun's light drowns out the little pinpoints of light of stars in daytime. And then the boy made a half revolution around the whiteboard representing a half a year, and now he could see the winter constellations, but then he made another about face and couldn't see the summer constellations on the other side. So just to throw in that idea. So here's some scripture verses about stars and constellations that I cannot help to append. Psalm 147:4 says that God knows the number of stars and calls them by name. Job 9:9 references Arcturus, Orion, and the Pleiades. So Arcturus is a star in Boötes, a very bright star. I think it's the fourth brightest, if I'm not mistaken. It mentions the Orion, and it mentions the open cluster, the Pleiades. Job 38:31-32 mentions the belt of Orion, the Pleiades, and Arcturus. And Amos 5:8 also references the Pleiades and Orion. Okay, here's a bonus and a concept check. This is a nebula, also known as a space cloud. It's not really a cloud. Nebulas occur when low-mass stars like our sun end its life. It blows up in a nova. It blasts off all of its layers into space, and what's left behind is a white dwarf in a nebula. Well, this is called the California Nebula because it's shaped like California. It's 1,000 light years away, and it's in the constellation Perseus. So the concept questions are, what's a light year? What does it mean by 1,000 light years away? What's a constellation? And how is a constellation different from an asterism? So you could go back to requirement 4 or this past requirement if you need help with that. Requirement 6 is do one of the following. Find a total of at least 5 asterisms and/or constellations in the sky. Or visit a planetarium or observatory. Now into requirement 7. Explain why the stars seem to twinkle and why the North Star is important in finding directions in the northern hemisphere. Well, the scientific term for twinkling is astronomical scintillation. Stars twinkle because their light is so small that the dust in our atmosphere keeps us from seeing it all the time. So little overlap from the weather merit. If you remember the hydrologic cycle, i.e. the water cycle, water is evaporated up into the air where it cools so that it could condense and form clouds. But it needs to have something to condense onto. In our atmosphere, there's dust, and so the vapors condense onto the dust particles in the air or our atmosphere, and the light from the stars has to go around that dust. Also consider that stars are like trillions and trillions and trillions of miles away. I mean, the nearest star, again, is around 4.2 light years, which is approximately 25 trillion miles away. And the light from that star and all the other stars have to travel through space, and it finally enters our atmosphere, but then it has to go around all the dust in our atmosphere. So that's why stars twinkle. However, planets don't twinkle, or at least much, because their light is so big enough to shine around the dust. Planets are super close relative to the stars, and they're reflecting light from the sun, and the sun's very bright. The sun is our nearest star. The sun is so bright, in fact, that 12 hours approximately you can't even see any of the other stars, or planets for that matter. So imagine this. Imagine that you're in a dark room and someone turns on a flashlight. Okay, now imagine waving your hand in front of the flashlight. You're going to see the light be bright and then dim and then bright so fast. So if you could just imagine that, that's like starlight going through the dust in our atmosphere. And then imagine the ceiling lights, or your bedroom lights, or classroom lights. Okay, and then try imagine waving your arm around that. Okay, you're not really going to cause such a dramatic twinkling compared to like the light from a flashlight. Okay, that's going to represent light from planets. And I've done this when I taught the Astronomy Merit in the past at Royal Rangers, and I did the same thing. I turned off the light, turned on my flashlight, and did that part, and likewise I turned on the big lights and did that part just for like some object lesson. Now what's this? It's not the Big Dipper. It is the Little Dipper. That's the asterism. But it's also the Ursa Minor constellation. Now I want your attention to be drawn to this star right here. This is a giant star. I'm not sure if it's supergiant or if it's just a giant, but it is a big star. It's called Polaris. These two are bright as well, so if you're like where I am in light polluted areas, you'll see these two stars and Polaris. But if you're in less light polluted areas, then you'll probably see these other four stars right here. But the point is that Polaris is called our North Star because it is above the geographical North Pole. Now this overlaps with compass. In fact, you probably learn astronavigation in the Compass Merit if you've taken it, because that's one of the requirements. You have the geographical North Pole and the magnetic North Pole. We're just focusing on the geographical North Pole. The North Pole is the top of the axis that goes through Earth from North Pole to South Pole, on which planet Earth rotates. Because it's above the North Pole, I believe that's also why they named it Polaris. Anyway, if you could imagine being on the North Pole and you're looking straight up, you're going to see this star. And all the other stars are going to go around Polaris. And I have a GIF for a little animation to help you make sense of that here in a few moments. But first, how do we locate this easily? Well, at any time of the year, you will probably see the Big Dipper, because the Big Dipper is a circumpolar asterism, which we'll talk about what circumpolar means later. But you usually see the Big Dipper all year round, at some point of the night at least. And if you take a look at these two stars, Meroc and Dubhe, these are the pointer stars that point toward Polaris. Okay, so all you have to do is just find the Big Dipper and find these two pointer stars, and it will point you toward Polaris. Just for a little trivia, this is a double star system right here. It's not one star, it's two, called Mizar and Alcor. And if you look closely, you could see with your unaided eye that these are two stars. In fact, thousands of years ago, this would be used as an eye test for the military. Like to enter the military, if you're going to be a good warrior, you have to have a good sight as well. And so this was used as a test. Now, in September evenings, the Big Dipper would be around here, versus in the late spring or early summer in June, versus this time of the year where it made it all the way around. So here's the GIF that I was talking about. Throughout the night, all the stars will rotate around this one star, and this one star is Polaris. And this occurs because Polaris is almost right above the geographical North Pole. The other stars, including Polaris, are known as circumpolar stars because they never rise and they never set. If you recall, the sun rises in the east, sets in the west, unless of course you're at either of the poles, and sometimes you have 24-hour day and 24-hour night, but other latitudes, they rise in the east and set in the west. Same thing with the stars. Well, there are some stars that are out all year long, day and night. They never rise above the horizon and they never set below the horizon. So they're called circumpolar stars. So here you see Ursa Major and Ursa Minor, well specifically the Big Dipper and Little Dipper asterisms, but you also see this 5-star system called Cassiopeia or Cassiopeia. As it rotates around, it's going to look like either an M, W, E, or 3. The reason I point that out is because that sometimes could help point out where the North Star is, especially if the Big Dipper is too low. The constellation Cassiopeia is a queen sitting on a chair, and nearby you could see Cepheus the king, as well as Draco the dragon, which kind of meanders between Ursa Major and Ursa Minor. And I invite you to look at a star chart to see the stars and how they're connected. You could also think of this GIF as snapshots of every day of the year at the same exact time. So if you go out and you take a long exposed picture for like 20-30 seconds so that you could get as many stars as you can at this time of the night, and then the next night you take another picture, and the next night you take another picture the same exact way, the same exact camera angle, the same exact time of the night, and then you put it all together in like a GIF or a flip book or something, this is also what you would see too. Okay, so the motion of the objects in the sky, specifically the stars, or especially the stars, depends on your latitude. So, in other words, in middle northern latitudes, the stars are going in diagonal, or in a diagonal fashion. So this is an incredible picture of circumpolar stars. Well, most of them are circumpolar stars. Some of them are rising and setting and such. But this was taken by long exposure photography. So the person, Daniel, apparently pointed his camera toward Polaris and then pressed the button, opened the shutter, and the exposure lasted for a long time. To do that, the camera had to be very, very still. And then once it was over, this is what it looked like. So it's a very neat effect. You can see that for however long the exposure was, the stars were traveling all around, and they were traveling all around this one point by the star Polaris. And you could also see that the stars next to Polaris, again, they're not rising and they're not setting. So here's a little, test, which one is the equator, which one is the North Pole, and which one is the mid-latitudes? Well, these stars are going horizontal, so that would be the northern latitudes. A big hint would be the northern lights right here, or aurora borealis. This one, you see that here's the horizon, and the stars are roughly vertical, not exactly, but they're roughly vertical, so this is at the equator, plus Polaris is right here at the horizon and such. So at the North Pole, Polaris is right straight up in the air, again a position of the sky we call the zenith. Opposite would be nadir, but for a little trivia, but if you're at the North Pole, you look straight up in the air, that's where Polaris would be. If you're at the equator or at the middle of the Earth, Polaris is like right by the horizon, and between the equator and the North Pole, Polaris would be somewhere between 0 degrees altitude and 90 degrees altitude. So this would be roughly 0 degrees altitude because it's right at the horizon, and then here would be 90 degrees altitude. But I understand if that's hard to grasp without a visualization or a graphic, so you could look that up. It's altitude. You could also look up azimuth and what that is. But anyway, the altitude of Polaris is going to change between the equator and the North Pole, so it would be somewhere between 0 and 90. Okay, so for something a bit extra and fascinating, Polaris will not always be our North Star. In fact, if you could imagine a top, like you spin a top, what happens? Well, the top wobbles. If you take a look at the top of the top, no pun intended, where you spin the top, that part that sticks up, imagine that being the North Pole, and it's going to wobble in a circle. Well, that's called precession, and spinning objects undergo precession. And so right now, the North Pole is pointing toward Polaris, But pretty soon, in like 13,000 years, well, if we'd be here, Vega, which is in the constellation Lyrae the Harp, part of the Summer Triangle, would be our North Star. And then 13,000 years later, or between 12 and 14,000, it would go back to Polaris. So here's a little video that shows that. Here, this represents Earth, and the needle right here represents the North Pole, and you see it's just passing Vega. As this object is rotating very quickly, it's going to continue to move, and soon it would go back to Polaris. Okay, so for a little brain break, here are the size comparisons of the planets and the stars. So we have Mercury, Mars, Venus, and Earth, and that's to scale. Now Earth, which is the largest of the terrestrial planets, is right here compared to the Jovian planets. Remember, there's about 1,300 Earths that could fit inside Jupiter, and about 1,000 Jupiters that could fit inside our Sun. So if you look up here, this is not our Sun, this is Proxima Centauri. Where have we heard that before? This is the nearest star to Earth other than our Sun. Our Sun's the nearest star, but this would be the second nearest star, 4.2 light years away. Here is Sirius, which is 8.6 light years away. This is in Canis Major, the Big Dog constellation, which is next to Orion. It's usually out during the winter, and this is the brightest star in the night sky. But here's Sirius compared to Pollux, which is one of the two bright stars of Gemini, Pollux and Castor. And this is Pollux next to Arcturus. Arcturus is in Boötes and is within the top 5 brightest stars of the night sky. And this is Arcturus compared to Aldebaran, the follower, if you remember earlier with the follower, the Pleiades, in the Taurus constellation. And then here's Aldebaran way down here compared to Rigel. Rigel is in the lower right of Orion. But here's Rigel compared to Antares. Antares is in Scorpius. It's a very bright red star. And a little trivia, Antares used to be mistaken for Mars because Antares is red in the night sky. But it twinkles, and it's part of a constellation, and it doesn't wander, so it's a star. So look at the name, Antares. What is the Greek equivalent or counterpart to Mars? Well, it's Ares. So Antares means rival of Mars. It's like, this looks like Mars, but it's not Mars, so we'll call it Antares. And so here's Antares compared to Betelgeuse, which is in the upper left of Orion. And this is classified as a hypergiant last time I checked. And in fact, it's I think somewhere between 400 and 600 light years away. Betelgeuse is on the verge of going supernova, or actually hypernova, which is probably going to create this great, magnificent cloud or nebula, just like the Crab Nebula, which was a supernova that happened about 1,000 years ago, or at least seen 1,000 years ago. And that would be so bright that it could be seen in daylight. And guess what? This is the most amazing thing about light years. The light of the supernova still has to travel all that distance to reach us. And if Betelgeuse is hundreds of light years away, then when this goes hypernova, we wouldn't know about it or see it for about several hundred years later. And what's fascinating is that when you look at a star, it might not exist because the light of its demise may not have reached us. In fact, what's too wild to think about is Betelgeuse may already have went hypernova, and we're still seeing it in Orion. Isn't that wild? I mean, it's possible that it might not exist right now, but we're seeing it with our eyes. That's just wild to think about. And here's Betelgeuse next to VY Canis Majoris, which obviously is in the constellation Canis Major. And for a long time, this was the largest known star. But somewhere in 2015, I looked, and they found about 6 more monsters bigger than VY Canis Majoris. The biggest one being UY Scuti, which is in the constellation Scutum. Now, a lot of these, especially the big ones, are systematic names, and systematic names are found all over science. And I believe they order them based on apparent magnitude or the brightness, and there's a lot of stars that are like alpha, beta, gamma, delta, and so on and such, and then the like the Latin or something of the constellation that it's in. Like Cygni, that tells me that this star NML Cygni would be in the Cygnus constellation, Cygnus the Swan, which is another constellation that is attached to the Summer Triangle. The third constellation is Aquila the Eagle, and again the first one I mentioned is Lyra the Harp. And these are the only ones that are discovered so far in our galaxy. In fact, all of these stars are in our Milky Way galaxy alone, not to mention all the other galaxies in this entire universe. I mean, every star that you see in the night sky comes from our Milky Way galaxy. The only time that we're seeing stars from other galaxies are when we just see the galaxy. Okay, so I have an additional brain break here, which is very interesting. This is referred to as our cosmic address. And so we're on Earth. The Earth is in the solar system. The solar system is in the Milky Way. The Milky Way is part of our local group. And our local group is part of our local supercluster. And there are tons and tons of superclusters in our universe, or I should say our observable universe. And yet there's no definite center of the universe. Some scientists call our local supercluster the Virgo supercluster. I've also heard Laniakea, which is Hawaiian for immeasurable heaven, which is quite befitting. Another thing is that the local group is also known as a cluster, and a cluster is just a group of galaxies that are bound together by gravity, and a supercluster is a whole bunch of clusters of galaxies that are bound together by gravity. In short, God is an incredible God. And speaking about stars, there are a couple of YouTube videos that you could watch, and it takes you from the smallest to the largest, like from Mercury to VY Canis Majoris, for example. I'm not sure if they updated it yet to UY Scudi, but it's fascinating nonetheless. Here's another picture of what I just said. You have Earth, solar system, Milky Way galaxy, our local group or cluster, our local supercluster, and observable universe. Let us now embark on the journey to talk about our neighbor, the moon, which is our nearest satellite. And hearkening back to the fourth day of creation in Genesis 1, and God created two lights, the greater light to rule the day and the lesser light to rule the night, and he made the stars also. Genesis 1:16. The moon has always intrigued and fascinated people and civilizations for millennia, and pretty soon mankind made it a goal to land on the moon, but it took a race called the space race to get there, which we'll talk about right now. Without further ado, let's start Requirement 8. Requirement 8 is sketch the moon's position in the sky on 3 different nights during a 1-week period. On one of those nights, sketch its position once an hour for 3 hours. So in the following slides, I'm going to walk you through a suggestion on how to do this. But to finish reading what the requirement says, answer these questions. A. Did you observe a change in the moon's position from night to night and hour to hour? B. What direction does the moon travel from night to night? C. What causes the moon to have different shapes called phases? That's what we're going to really focus on in this requirement after talking about the space race. And D. What causes the moon to move in the sky during the night? Well, I'll go ahead and answer part D. You're welcome to pause if you want to think about it. But when you go outside and you see the moon somewhere, maybe the east, southeast, or south, or southwest, or west, wherever you see it, you're going to see the moon travel toward the west and eventually set. The reason for that observation is primarily because Earth is rotating. However, the moon is also revolving around the Earth, which we'll talk about here shortly too. So, truth be told, I didn't earn the Astronomy Merit. I was a little bit interested, but not totally interested until 2015, before I taught the Merit for the first time and took a class at my college. But in the summer of 2015, this is what I'd done. Now it's a bit overkill, and this isn't what the Merit requires, but I used this as an example when teaching about the lunar phases to my boys at my outpost the past 3 times I taught it. So what I did is I drew my house and the surrounding houses and trees and telephone poles, And then I marked an X at the end of my driveway, right between the driveway and the grass. I've written out the coordinates, like west and east, and then south over here, so north is behind me. And at the same exact time, every single night, 8:30 p.m., I went out and I took a look at where the moon was and what phase it was in. And I just drew exactly where the moon was. Likewise, you have to do something like this, but only 3 days. And then on one of those days, you have to draw the moon 3 times, once an hour. So here's something to help you out. This is something I made and printed out and gave each boy 3 copies. The past 2 times I taught this, but you could design it however you want. I just encourage you to take out a blank sheet of paper, draw the horizon line and such, and then draw your house. And then draw your neighbors' houses and any like buildings or trees or mailboxes, any landmarks like that. And then I want you to draw an X at the exact spot you're going to look, and you're going to be facing the same direction. And make sure that you write the name, the date, and the time you went out. Now let's say on the first night the moon is right here. Well, you would just draw the moon exactly where you see it, so it would be above this tree, and this is what the phase is. It's a sliver. It's called a crescent. We'll talk about that. Well, you just do that and you're done for the first night. Now you could go out the next night or 2 or 3 nights, and maybe the moon is right here, and it's probably a bit more illuminated, and again we'll talk about that. And then in a few more nights, the moon may be over here, and it's even closer to being full. This is a phase known as the gibbous. And on this night, preferably when the moon is somewhere over here, this is a good time for you to go out 3 times tonight. So next to your drawing, you would write the time, and then 1 hour later, go out at the same spot, and the moon would probably be over here. So you would just draw it out exactly where you see it and write down the time, and likewise do it 1 hour later, and then write down the time. It's best to do this one where you're out once an hour for 3 hours when the moon is in a gibbous phase or a full phase, because you're guaranteed to see it in the span of that time, barring any clouds. If you'd done it the first night when it was over here, then after the first hour it probably would have set. So just wait till it's this time of the lunar month. So that's just ideas to get you started. Do so and show your commander. Now I want to talk about the famous space race, and you may have heard about this before, but what was it? It was a race between the Soviets and the US to get out into space, to send satellites out there, living things out there, and ultimately mankind out there. And the Soviet Union is now Russia today, and you also notice that the United States flag has 48 stars because in the late 50s, the Union had 48 states. So here's a replica of Sputnik 1, and this was the first satellite in space, and it was launched on October 4th, 1957. And it was the Soviets that won this one, so the Soviets won in getting the first satellite into space, and Sputnik is Russian for satellite. However, the US launched Explorer 1 the following year, and this was the first satellite from the United States into space. And then here's the model of Sputnik 2, and this was launched on November 3rd, 1957, and you guessed it, it was the Soviets that launched this one. But this one was a bit different. It actually carried a dog in it, and this is Laika, which became the first living animal to orbit Earth. Unfortunately, they did not know how to get the satellite down, and Laika died in space. Now it was on to getting man out in space, and that first man was Yuri Gagarin. He was the first human in outer space and to orbit Earth, and he was a cosmonaut. The term cosmonaut gives you a hint that it was the Soviets that won this time, and he was launched in Vostok 1 on April 12th, 1961. And Vostok is Russian for east, just to say. But to analyze the term cosmonaut, the cosmos refers to the universe, kind of a bit like that series, The Cosmos, or actually 2 series. But anyway, what an astronaut is to the United States, a cosmonaut is to the Soviet Union and, well, present-day Russia. So it means the same thing, just a man out in space, above our atmosphere, but just 2 different words. And astronaut, astro means star, cosmo means universe, just A little trivia there. Anyway, but that didn't stop the United States from sending a man out in space, and that was Alan Shepard. He was the first American in outer space, and he was launched on May 5th, 1961 on Freedom 7. And now here's John Glenn. And John Glenn was the first American to orbit Earth, 3 times in fact. And he was launched on February 20th, 1962 in Friendship 7. Now he went on to become a senator, and then when he got older, like in this picture, he went back into space. I'll actually never forget December 8th, 2016, coming home from OCC and hearing the news, I believe on the radio, of his death, and that was all over the news at that point. Now onto the huge, monumental goal of them all, land a man on the moon. Now, the Soviets won in sending the first satellite, sending the first dog, sending the first human, but they have not yet landed on the moon. John Fitzgerald Kennedy, our 35th president, was a huge proponent within this space race, and you could actually go on YouTube and watch videos of John F. Kennedy talking about the perseverance of landing on the moon and not giving up. In fact, let's listen to John F. Kennedy at Rice University in 1962.
But it will be done, and it will be done before the end of this decade. And I am delighted that this university is playing a part in putting a man on the moon as part of a great national effort of the United States of America. But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
And unfortunately, JFK could not see that dream come true, for he was assassinated in Texas on November 22nd, 1963. And then it happened. Apollo 11 in July of 1969. Here you have Neil Armstrong. I'll never forget hearing when he died in 2012. Michael Collins, who never actually landed on the moon. He stayed in the spacecraft and orbited the moon. And then Buzz Aldrin. And here's some pictures of the moon landing. Here's the famous picture with our American flag planted on the moon. Now, just to dispel any opinions about the waving flag, the flag isn't actually waving. There's wires inside of here. The moon does not have enough gravity to hold an atmosphere. It's kind of a bit like Mercury. Again, the moon's gravity is 1/6 that of Earth, so you could jump 6 times higher. That's why you could see video of astronauts jumping like 6 times higher than on Earth. There's no wind because there's no atmosphere, or hardly any atmosphere, and therefore there's no way for a flag to be waving, so they just put wires in here to make it look like it's waving. Here's another famous picture. And because there's no wind, these footprints are said to be there forever, and they're probably still there over a half a century later.
20th, 1969.
It's one small step for man, one giant leap for mankind.
So now let's talk about the moon. So you have a lit side, and you have the unlit side, unless of course it's a full moon. This line right here is called the terminator, the line that divides the light side from the dark side. You can fit every other planet in our solar system between the Earth and the moon and still have almost 5,000 miles to spare. The average distance is approximately 238,900 miles. So here's some fast facts. The moon obviously is orbiting Earth and therefore has an orbital velocity. Just like the Earth goes around the sun at 67,000 miles per hour, the moon is going around the sun at 2,288 miles per hour. It's approximately 1 light second away, which means that every time we see the moon, we are looking back in time 1 second. It shines by reflected light, which means that when we see the moon, we don't see it because it's producing its own light. The light from the sun bounces off the moon, or reflects, and that's why we see the moon, as bright as it is. More on that later. But put in another way, it just means that the light bouncing off from the moon takes 1 second for it to arrive here on Earth. But to get a bit more technical, the light from the sun traveled over 8 minutes to reach the moon in the first place, and then another second just to reach Earth. The temperature ranges from negative 280 to 260 degrees Fahrenheit, and this is where we get the words Monday for moon, just like Sunday for sun, as well as month or month. Think about the Spanish word for moon, which is la luna, which we'll get to here in a few seconds. But think about the Spanish word for Monday. The Spanish word for Monday is lunes. And speaking about luna, that's how we get the word lunatic. People are said to go crazy under the influence of a full moon, and they call them lunatics. That's why. Now this is very neat. Take a look at the orange dots and say aloud which one is bigger, the left or the right. I would probably say the right one's bigger. Actually, no, they're both the same exact size. But this one, well, or at least to most people, looks bigger than that one. And I'm making a point of this because of something known as the moon effect. The moon looks large when it's rising and small when it's high in the sky, but they're the same exact size. So for example, let's say the moon is up here. Now, let's say the moon is down here. When the moon is down here, in our field of view, it looks bigger, right, than up here. Well, they're the same exact size. So going back here, let's say that the large blue circles represents all the open space up in the sky. So you look up and you see all the space around. Well, when you see the moon with just a little bit of sky around it, and then a lot of buildings or trees down here, it looks bigger. But what you could do when you see the moon rising, you could take your thumb or a coin and hold it up so that it covers the moon, and then remember that arm distance, and then go back a few hours later when the moon is high in the sky and do the same thing, and you'll see it's the same exact size, even though when it's by the horizon it looks bigger. Now, what causes the lunar phases? Is it the Earth's shadow being casted onto the moon? Just like this? Well, what about these phases over here? And if the sun is right here, how on earth could the shadow be going this way? Therefore, it's not Earth's shadow that causes the lunar phases, it's Earth's shadow that causes lunar eclipses, but not the phases. So what causes all of these different phases that you see here? Well, here's the definition I came up with, and then I'll explain. Essentially, it's the position of the moon along its orbit around Earth, it's our perspective here on Earth, and it's the angle between the sun, Earth, and moon which dictates the lunar phases. In other words, the sun is right here. The moon is in a certain position around Earth at any given time, and Earth is right here in the center, or at the vertex. So the angle between the sun, Earth, and wherever the moon is in its orbit tells what the lunar phase will be. Let's look at this example right here. When the moon is here in its orbit, this is what the phase looks like, a waning gibbous. And again, we'll break down as to why this is. Important note, the moon is always half lit, but we're always seeing one half of the moon. In other words, the sun is right here, and it's shining in this direction. Okay, the moon, as you see here, is always half lit. But since the moon is a sphere, we could only see one half of it at any time. So here's another picture, but this time we're behind the sun, and here's the moon, and here's Earth. Now as the moon goes around the Earth counterclockwise, the moon is half lit by the sun, and the other side is unlit. And in this perspective behind the sun, we're seeing the lit side. So over here, the moon is always full. If you're on Earth, right here in North America, or wherever you're at, facing the sun, you're only looking at the dark side of the moon. The lit side is on the other side. If you're on the other side of Earth and you're looking outward, you're looking at a full moon. And anywhere in between, you're going to see a partially lit moon. But again, the moon is always half lit, so we'll be talking about that here right now. But again, real quick, in its orbit, the moon is right here, between the Earth and the sun. The sun shines on the moon, making half of it lit and half unlit, and the unlit side is facing Earth. That's why we have the new moon. So here's an animation similar to what I'm talking about. The moon is right here in front of Earth, and we're seeing the dark side, and the lit side is on the other side because it's being lit by the sun. This is also how solar eclipses work as well. So here's another illustration that I made copies of and handed out to the boys, and obviously it's not like a book perfect illustration with perfect circles or anything, but it's just to get the idea. If you want to, I invite you to pause now and draw this out if you want to follow along that way. And so let's get started. So we already talked about the new moon. The new moon is a result of the moon being in front of the sun. So think about it. For the moon to be in front of the sun all day long, that means it needs to rise with the sun. And if the sun rises around 6 a.m. and sets at 6 p.m., that means the new moon rises at 6 a.m. and sets at 6 p.m. typically. Not perfect, but just a rule of thumb. So the first quarter moon rises at noon, sets at midnight, roughly. So we're skipping this phase and we'll get back to it. And this is what causes the first quarter moon. So recall that the moon is always half lit, and we're only seeing half of it at any time. So I'm going to make these illustrations. You don't have to do it on your piece of paper if you chose to copy this, but I'm going to draw a line between the sun and the earth, and another one from the earth to the moon representing our perspective. Now remember that the moon is always half lit and half dark, and we could only see one half of the moon at any one time. So I drew what's called a perpendicular line, and this right here is the half that we see. And as you see here, half of it is lit and half is unlit. And that's how we get the first quarter moon, because of our perspective here on Earth. Here's another illustration to show this. Here the sun, earth, and moon make a 90-degree angle. Okay, now the waxing crescent moon. First of all, why is it named waxing? It's because waxing means growing. From new moon to full moon, the illumination is growing bigger and bigger. And crescent refers to the shape. It's shaped like a crescent or like a croissant. So what causes this? I'm going to draw a line from the sun to the earth, and then from the earth to the moon. Now remember, the moon is always half lit, but we could only see half of it at any one time. And after drawing the perpendicular line, you could see that you have a little piece that's lit and a large piece that's unlit. And that's exactly what you see with the waxing crescent. Now, I want you to take a look at this picture, and you see this ghostly image of the dark side of the moon as if it's lit up, and this is called earthshine for a good reason. So what causes earthshine? Well, bear in mind that if you're on the moon, you could see Earth, but the Earth isn't producing visible light. Just like all the other planets and satellites, it reflects light. So recall that the Earth is much more massive than the moon, and therefore reflects the sunlight about 50 times more bright than the moon does. So when you see Earth shine, this is literally light that bounces off the Earth from the sun and hitting the moon. And since we only see a little bit of the illumination, that's why we're able to see it the way it is. Now onto the waxing gibbous moon. So gibbous means hunchback, and this is your egg-shaped moon. It is the result of the moon being right over here, making this what we call an obtuse angle, because it's greater than 90 degrees. So it bears repeating. Remember, the moon is always half lit, half unlit, and we can only see half of it at any one time. So I'm going to draw the line from the sun to the earth, and from the earth to the moon, and now I'm going to draw in the perpendicular line, and you see that you have a lot of it lit and just a little bit unlit. And that's exactly what we see for the waxing gibbous moon. And again, that's because the angle between the sun, earth, and moon is greater than 90 degrees. If it's equal to 90 degrees, we have the quarter moons, and if it's less, we have the crescent moons. Okay, now on to the full moon. This is kind of the opposite of the new moon. In lieu of the moon being directly in front of Earth, well, not directly unless it's a solar eclipse, the moon is behind the Earth. And if you think about it, the sun and moon are on opposite sides of each other. But bear in mind, the sun is like 400 times farther away than the moon is. So this means that at the time the sun sets, the moon is rising. And by the time the moon sets, 12 hours later approximately, that's about the time the sun rises. So it rises approximately at 6 p.m. and sets approximately 6 a.m. and it's highest in the sky at noon. And so here's my picture that I took one early morning on May 11th, 2017. And then that night, it was kind of a bit of a waning gibbous, so you could barely see that it's not exactly full. And again, this was almost 9:30 at night, the same night. So let's talk about the waning gibbous. It's pretty much the same exact thing as the waxing gibbous. It's just that the lit side is going to be on the other side. But first, what does waning mean? Waning means shrinking. So waxing means growing, waning means shrinking. During this half of the lunar month, about 2 weeks, the moon is waxing from new moon to full moon, and in this latter half, in this remaining 2 weeks, it is waning from full moon back to new moon. But once again, it's the same process. I'm drawing the line from the sun to the earth, and then from the earth to the moon. And as you see right here, you have a lot of the illumination on the lit side and a little bit of the unlit side. And that's why we have the waning gibbous. Here's a picture of the waning gibbous. It does rise approximately 8:30 to 9:30-ish. And what's neat is on September 30th, 2015, I was just starting to teach the lunar phases for the first time to the Discovery Rangers at my outpost. And then as I was leaving Rangers that night, about somewhere between 8:45 and 9, I see this rising over in the east. So I take a picture and I show it to the boys. And I'm like, did you see the moon? This is what we were talking about. Okay, now the last quarter. And once again, it's like opposite the first quarter. And it's caused by a 90-degree angle. It's just the illumination is on the left side. And you have to be up pretty late to see it. The first quarter moon rises at noon, sets at midnight, while the last quarter moon rises at midnight and sets at noon. So how do you tell the difference between the last quarter and the first quarter if you're just to look at a picture? Because I hope that you know now that if you're up and you see a moon that apparently looks half lit and half unlit like this, and it's like 1 in the morning, then you know it's the last quarter moon. But let's say that you look at a picture and you were told that it was taken in the northern hemisphere, then how would you be able to tell which one's the last quarter and which one's the first quarter? One of the simplest ways I could think of is to think about the letter L. Okay, the illumination is on the left side. Left begins with L, and it's the last quarter moon, and the word last starts with L. Furthermore, and this is what my first and second grade teacher taught us when I was about 6 or 7, is that she remembers it as the letter L. She associates that when writing the L, you have the vertical stroke on the left side, kind of a bit like the illumination being on the left. But if you think about the illumination being on the left side that starts with L along with L for last, then I think you're good to go. And finally, onto the waning crescent moon. Again, the same exact thing for the waxing crescent, but just opposite. It's formed by an angle that's less than 90 degrees, and we call that an acute angle in geometry. And I just want to append that it rises at 3 a.m., so unless you're an early riser, you hardly see the waning crescent moon bright like this, unless of course you're out very early in the morning, which actually happened on November 5th, 2015. I went out and it was past 5 a.m. and I looked toward the east, and lo and behold, there was the waning crescent moon. And to me personally, it was kind of incredible because I am so used to seeing a crescent moon where the illumination was more on the other side, but that's just me. I might as well say now, you probably are wondering, how is it that we sometimes see the moon in the daytime? It's because the moon rises very late at night or very, very early in the morning, and the moon is out for approximately 12 hours, like our sun, and by 9 a.m., the waning crescent moon would be at the highest most part of the sky, and then it would set at 3 p.m. So it's usually the waning phases when you see the moon in the morning or later in the day. For instance, you could expect the waning gibbous to be setting approximately at 9 a.m., the last quarter at 12 p.m., and the waning crescent at 3 p.m. So the rule of thumb is 3 hours difference for all of these times. Also, why is it called the first quarter and the last quarter moon when it's half lit in our perspective? Well, that just refers to the lunar cycle. The first quarter moon is 1 quarter through the lunar cycle, and the full moon would be 2 quarters or 1/2, and the last quarter begins the final 1/4 or the final quarter of the lunar cycle. And so that's our tour of the lunar phases. So here's a rule of thumb. From new moon back to new moon is approximately 30 days, or about 4 weeks, a little over 4 weeks. The rule of thumb is that each quarter of the cycle takes about 1 week. So for example, from new moon to first quarter takes about a week. From first quarter to full would take another week. which means from first quarter to last quarter is about 2 weeks, from new moon to last quarter is about 3 weeks, and so on. So when determining what the lunar phase is, when you're looking at a picture, or if you're outside and you see the moon and you're trying to determine what the lunar phase is, you have to ask yourself, is it new or full? If it's a new moon, you wouldn't be able to see it anyway, and if it's a full moon, you would most definitely know about it. Here's the full moon there. If not, is it a crescent, quarter, or gibbous? So a crescent is the sliver, a quarter is where, in our perspective, we see half of it lit and half unlit, and the gibbous is more of the egg shape. Then ask yourself, is the illumination on the right or on the left? Well, if the illumination is on the right, then that means it's waxing. If it's on the left, that means it's waning. Think about left. Okay, left begins with L, last begins with L, and the last quarter is in the waning half. So essentially it's asking, is it waxing or waning? So here's a little GIF animation showing this. It goes from new moon all the way around to the quarter moon to the full moon. And over here is what you would see in your perspective on Earth. So a little test to now apply your knowledge. What lunar phase is this? You could feel free to press pause. Well, is it a new moon or a full moon? No, you could see it, and it's not yet full. So you have to ask, is it a crescent, quarter, or gibbous? Well, this is a gibbous. Now, is the illumination on the right or on the left? The illumination is on the right side. Therefore, it's waxing. This is the waxing gibbous moon. The reason why I was saying earlier about provided that was in the northern hemisphere is because when you're in the southern hemisphere, everything is upside down, including the constellations. The Orion is upside down and such. And that's just because you're below the equator. Here's an activity that I did the first round I was teaching this, and it's using Oreos to craft out the different lunar phases. And I would give each boy 2 phases and 2 Oreos and put them up to the test. So here's the familiar face of the moon that we always see, and here is the other side of the moon that we don't see. And now we're going to talk about why we never see this side. There are 2 main types of revolutions of the moon. First, it takes the moon 27.322 days to revolve around the Earth. And it takes about the same amount of time for it to rotate once on its axis. This is called the lunar sidereal period. So if you notice, the moon is orbiting Earth, at the same time it's rotating on its axis. So the same face of the moon faces the Earth all the time. And that's why we always see the same face of the moon. So now imagine hovering over the north pole of the moon for an entire rotation of the moon and revolution around the Earth. This is what you would see. Furthermore, the lunar phases takes 29.531 days to cycle through. This is called the lunar synodic period. Here's a couple of pictures that I like of the moon in front of the Earth. Here's the North Pole and here's the South Pole. Here is what's called the moon calendar, and it shows the phases on a particular day of all the months of the year for the year 2017. Now this goes by every 2 days. So if this is January 1st, this would be the 3rd, the 5th, the 7th, and so on. Okay, so what causes lunar eclipses? Well, lunar eclipses occur when the Earth's shadow falls on the moon. That happens when the moon is directly behind Earth, enough to fall inside the shadow. A solar eclipse, on the other hand, is when the moon is in front of the sun, casting a shadow on Earth. However, how is it then that every time we have a new moon, we don't have a solar eclipse, and every time we have a full moon, we don't have a lunar eclipse, also known as a blood moon? Well, it's because the moon has a 5.2 degree orbital tilt right here. So if you take a look over here, here's where the new moon is, and it's a new moon because it's in front of the sun, and you see the shadow doesn't fall on Earth because of this tilt of the plane. And same thing with a full moon. The Earth's shadow doesn't fall on the moon right here. Same thing over here. And this is the side view right here. Here's where the moon would be, new moon and full moon. Here's a close-up picture. However, over here, it lines up right here between the sun, moon, and Earth. And that's because the moon crosses these nodes right here. And that's how we get eclipses. And here's a couple of pictures that I took of the blood moon. Here's a time-lapse GIF of the blood moon forming, and here's the reason why lunar eclipses turn the moon red. The sun's light travels past our atmosphere and falls on the lunar surface. In essence, it is reflecting the light of all Earth's sunrises and sunsets at the same time back to Earth, appearing blood red in color. Okay, requirement 9. Do one of the following. A. With a small telescope or binoculars, study the moon, stars, and planets on 3 different nights. Keep notes to compare what you observed each night when identifying each object. Or B. With the aid of an astronomy book, star chart, or website, make drawings of the northern and southern skies as they look for the current season of the year. So if it's autumn where you're at, look up the star chart for autumn nights for the northern and southern hemisphere. And write at least 5 major constellations placed in their proper positions. Requirement 10. Give 3 scripture references regarding the stars, moon, planets, sun, constellations, etc. The image that I chose in the background is the cross in the Whirlpool Galaxy, and the picture was taken in 1992. Truly the heavens declare the glory of God, which is a good scripture verse. In fact, if you've watched my previous merit videos in the past, I usually introduce you to the concordance in case you don't know what a concordance is yet, and give you some keywords. But for this merit, you're welcome to do that, but I just cannot resist, and I invite you to look up all of these. Psalm 19:1, Psalm 33:6, Genesis 1:1 and 16, 1 Corinthians 15:40-41, Psalm 148, 1-4. Also, there were those scripture passages when we talked about the stars and constellations and when we talked about Hubble that I shared here. What I encourage you to do is reread through all of them and just pick out your favorite 3, or you might find another one yourself. Okay, so the very last thing that I want to append, something extra, is the origin of the days of the week, in case you're curious about that. Sunday comes from sun, Monday comes from moon. The Spanish word for Monday is lunes, so remember lunes, luna, which is Spanish for moon. Tuesday comes from Mars, or Tyre, which I'll get to in a second. The Spanish for Tuesday is martes, so martes, Mars. Okay, but Tyre, who's that? Well, in English, most of the days of the week comes from Norse mythology, not Greek or Roman. Norse means north, so the followers of Norse mythology lived in Northern Europe, in the Germanic countries, such as where Germany is today, north of Italy and Greece. And Tyre is the Norse counterpart of Mars. He was also the god of war. Wednesday comes from Mercury. In Spanish it's miércoles, so miércoles, Mercury. And in Norse mythology it's Woden, also spelled out as Odin. So it's Woden's day, which was morphed into Wednesday. That's where we get that. But Mercury and Woden aren't counterparts according to my research. Thursday comes from Jupiter. In Spanish it's Jueves, so Jueves, Jupiter. And the Norse god is Thor, so Thor's day or Thursday. In fact, Thor was the chief god that created the thunder and the lightning according to the mythology. Same thing with Jupiter, same thing with Zeus. And talking about the Germanic countries like Germany, the German word for Thursday is Donnerstag. Okay, Donner is German for thunder. Do you remember a couple of characters named Donner and Blitzen? They were a couple of Santa's reindeer. Well, Donner means thunder in German. Blitzen means lightning in German. So Donner and Blitzen, thunder and lightning, just a little trivia there. And also talking about German, Sunday in German is Sonntag. So Son, like sun, and German for Monday is Moontag. Okay, Friday comes from Venus or Viernes. And in Norse mythology, it's either Frigg or Freya, and their counterparts. But long story short, it's unknown whether these are the same goddesses, Frigg and Freya, if they're one and the same. And Saturday from Saturn. Okay, so big congratulations. You got an outstanding start on the Astronomy Merit. The next thing is to show your commander the notes, do all the projects and research at home, and you should be well on your way. So once again, great job.